Welcome to the Sleepy Scientist. I'm glad you're here, and I hope wherever you are in the world you've found a little pocket of calm to unwind. Whether you're settling into bed, curling up on the couch, or just letting your mind drift like a telescope on a lazy swivel, this video's here to keep you company. Tonight, we're going to explore Starlight, not just how it sparkles, but how it speaks. Because believe it or not, every glimmer in the sky is a message from deep time, travelling across light years to reach your eyes, or in this case, your ears. Before we begin, I'd love to know where you're watching or listening from, and what time it is where you are. There's something cozy about imagining people all over the world looking up at the same sky, just at different times of night. Let me know in the comments. It's one of my favourite things to read. And if you find this video soothing or interesting, or ideally both, please consider giving it a like and subscribing to the channel. It really helps this sleepy little corner of the internet grow. Now, fair warning, this video might be a touch too fascinating to fall asleep to, but if you do end up wide-eyed at midnight pondering hydrogen absorption lines, well, at least you'll be smarter for it. So, close your eyes if you'd like, take a deep breath, and let's float together into the gentle mystery of Starlight. And finally, before getting underway, this video is for educational and relaxation purposes only, and is not intended as medical advice. What is Starlight, really? It's one of those things we've grown up with, something so familiar we often forget how strange and wonderful it truly is. It twinkles above city skylines and glows silently in country skies, scattered across the blackness like cosmic breadcrumbs. Poets write about it, lovers wish upon it, and astronomers stare at it for years on end. But beneath the romance and the mystery, there's something very real, very physical happening. Starlight is not magic, it is science at its most elegant, a glowing message flung across space. At its heart, starlight is energy. Specifically its electromagnetic radiation, the same broad family of energy that includes the warmth from a campfire, the hum of a microwave, and the invisible beams that carry Wi-Fi through your house. Light is just one slice of this vast electromagnetic pie. The light we can see, known as visible light, is a tiny sliver of a much bigger spectrum. Some of that spectrum gives us sunburns, some heats up leftovers, some bounces off satellites and lands in your phone as cat videos, and some of it, the most poetic part, journeys across the universe to whisper to us about distant suns. What we call starlight is mostly visible light, but stars don't limit themselves to that. They emit infrared, ultraviolet, and even X-rays and radio waves depending on their size, age and mood. Stars are not picky. They radiate across the whole electromagnetic spectrum, but we notice the visible part most because that's what our eyes evolved to detect. Probably because it's what the sun, our local star, produces in abundance. When a star shines, it's not doing it out of politeness. It's the result of intense physical processes at work. Deep in a star's core, hydrogen atoms are smashed together under unimaginable pressure and temperature. They fuse into helium, releasing enormous amounts of energy in the process. This energy radiates outward, colliding with other particles, bouncing around, and slowly making its way to the surface. Once it escapes the star's outer layers, it becomes what we see as light. But this isn't just a warm yellow glow like a bedside lamp. Stars are far more complex than that. They radiate light in a spectrum, a continuous range of colours from red to violet, with each colour corresponding to a specific wavelength of light. The full rainbow of light a star emits is called its blackbody spectrum, and despite the name, it's not about anything being black. A blackbody is an idealised object in physics, something that absorbs all the radiation that hits it, and then re-emits it perfectly based on its temperature. Real stars behave pretty similarly to these theoretical blackbodies. The spectrum of light they emit forms a smooth curve when plotted on a graph, with a peak that shifts depending on how hot the star is. Cooler stars, though cool is very relative in space, emit more of their light in the red and infrared part of the spectrum. These stars glow with a soft orange or red hue, and are often smaller and longer lived. On the other end, hotter stars pump out more blue and ultraviolet light. They shine a bright icy blue and tend to burn out faster, living fast and dying spectacularly. This spectrum tells us something very important. Light isn't just brightness, it's information. Every wavelength carries a clue about the star's temperature, its size, even what it's made of. You could think of a star's light like the chords in a song. Each one is made of many different notes, and if you know how to read the music, you can understand everything about the piece, from the key it's in to the instrument playing it. Now, light doesn't just fly out in all directions and disappear. It's made up of photons, tiny packets of energy with no mass and no charge. These photons are born in the star's core, like passengers getting on a very crowded subway. They jostle their way outward, sometimes taking thousands of years just to reach the surface. Once they're free, they travel at the fastest speed the universe allows, just under 300,000 kilometers per second. Photons are tireless. They don't slow down, they don't age. If nothing stops them, they can travel through the cosmos forever. Some of the starlight reaching your eyes tonight might have left its home before the first human walked upright. You're not just seeing a light in the sky, you're witnessing the past arriving in real time. There's something quietly beautiful about that. Starlight is time travel, just moving in one direction. A star 500 light years away is showing us what it looked like 5 centuries ago. A star in the Andromeda galaxy is shining with light that began its journey 2.5 million years ago, back when our ancestors were just figuring out how to use stone tools. The night sky is a gallery of ancient portraits. But let's come back to the nature of this light. Why do stars shine in different colours? Why are some stars red and others blue or white? It all comes down to temperature. Just like a metal rod glows red when you heat it up, stars glow with different colours based on how hot they are. A red star is cooler than a white or blue one. Our own sun is somewhere in the middle, yellowish, with a surface temperature of about 5,500 degrees Celsius. Colour isn't just aesthetic, it's a cosmic thermometer. And thanks to black body radiation and some clever physics, we can estimate a star's surface temperature just by analysing its colour. There's no need to fly a spaceship up close with a giant thermometer. The light carries all the information we need. But of course real stars aren't perfect black bodies. Their light isn't a completely smooth curve. There are interruptions, dark lines where certain wavelengths are missing. These are called absorption lines, and they occur when atoms in the star's outer layers absorb specific energies. Each element has its own set of lines, like a chemical signature. So when you look at a star's spectrum, it's not just a blur of colour. It's a detailed barcode that tells you exactly what's inside. That's the poetic side of starlight. It is both the glow of a fire and the fingerprint of a furnace. It is not just the light that reaches us, it is the story hidden in that light. Even the brightness of starlight tells us something. A dim star might be far away, or it might just be small. A bright star might be nearby, or it could be enormous and burning intensely from afar. By comparing a star's apparent brightness with its actual energy output, what we call its luminosity, we can estimate how far away it is. Light becomes a ruler stretched across the cosmos. The more you think about it, the stranger it becomes. We know so much about these massive nuclear fireballs floating in space, and yet we've never touched one. We've never been near one. Everything we know, every fact about their temperature, composition, size, movement, age, it all comes from starlight. Just light. No samples, no visits, just photons, decoded carefully and patiently over centuries. And perhaps that's what makes starlight so enchanting. It's honest. It doesn't hide anything. It just travels, carrying a little bit of the universe with it. Every time you glance up at the stars, you're bathing in ancient messages, particles of light that have travelled unfathomable distances just to land, quietly and without fuss, on your eyes. In a world filled with noise, there's something soothing about that. A silent, glowing language written across the cosmos. Not shouting, not demanding, just patiently shining. Waiting to be understood. Imagine a photon being born deep inside a star, a tiny packet of light energy with absolutely no mass, no charge, and no plans of ever stopping. It begins its life in chaos, smothered by roaring plasma, jostled by particles bouncing in every direction like a child in a ball pit. This little photon's journey is anything but straightforward at first. In fact, it can take tens of thousands, even millions of years just to travel from the star's core to the surface. It's a staggering thought. By the time that Photon escapes the outer layers and begins its cosmic voyage, entire civilizations may have risen and fallen on a distant orbiting rock. Once it finally breaks free of the star's surface, the photon enters open space. A realm so empty it's almost difficult to describe. If you took the average cubic meter of interstellar space, you'd find just a handful of particles, maybe a stray hydrogen atom or a bit of dust, but mostly it's just vacuum. This emptiness is perfect for a photon. After all that bouncing and wrestling inside the star, it now gets to stretch its metaphorical legs and coast in a straight line, uninterrupted at the speed of light. This speed, nearly 300,000 kilometers per second, isn't just fast, it's the ultimate speed limit of the universe. Nothing outruns light, and nothing really needs to. At that speed, a photon can circle Earth over 7 times in a single second. But photons aren't just zipping around our planet. They're crossing the gulfs between stars and galaxies, often for millions or even billions of years. It's not exactly a quick commute. Once in space, photons do something rather lovely. They stay the course. Unless acted upon by gravity or matter, they travel in perfectly straight lines. They don't get tired. They don't slow down. They don't age in the way we understand time. In fact, from the photon's point of view, time doesn't pass at all. For us, the light from a star might take 100 years to reach Earth, but for the photon that journey is instant. It's as though it blinked into existence in a star and blinked out again in your eye, without ever noticing the wait in between. But while space is mostly empty, it's not completely empty. Along the way, photons can encounter particles, gas clouds, or cosmic dust. When they do, a few different things can happen. The photon might scatter, getting knocked slightly off course. It might be absorbed entirely, never making it to its original destination. Or, in some cases, it might pass through unbothered, especially if it's energetic enough or travelling through clearer regions of space. Cosmic dust might sound romantic, like something glittering in the void, but it's actually a nuisance for light. These tiny grains, often made of carbon, silicon, and ice, float through space like microscopic snowflakes. In dense regions like nebulae or the crowded disks of galaxies, they can block or scatter light, especially the shorter blue wavelengths. This is why distant galaxies sometimes look reddish. Their blue light has been scattered away, leaving only the longer, redder wavelengths to reach us. It's also the same reason sunsets on Earth are red. The atmosphere scatters blue light more effectively. But even when photons dodge all the dust and debris, they still have another obstacle to contend with: gravity. Now, gravity doesn't tug on light the way it does with objects that have mass. But Einstein's general theory of relativity tells us that gravity isn't just a force, it's a curvature of space-time itself. And photons, despite having no mass, still follow the curves. Imagine placing a bowling ball on a trampoline and watching how the surface dips. Now roll a marble past the bowling ball, and you'll see it veer along the curve. That's essentially what happens when light passes near a massive object like a star or a black hole. Its path bends, not because it wants to, but because the space it's moving through is bent. This bending of light is called gravitational lensing, and it's one of the more elegant ways the universe reveals itself. When a massive object sits between us and a more distant light source, it can magnify, distort, or even multiply the image of that background source. We've seen galaxies appear as rings, arcs, or strange mirrored shapes, all thanks to the bending of light by gravity. Gravitational lensing is not just beautiful, it's useful. It allows astronomers to observe galaxies that would otherwise be too faint or distant to detect. It also helps map the invisible, dark matter. Since we can't see dark matter directly, we use the way it bends light to figure out where it is and how much of it there might be. In a way, it's like watching ripples in a pond to guess where an invisible stone might be sitting. But for all its encounters with gravity and dust, the majority of starlight travels largely uninterrupted through space. And this is where the magic really begins. Because as that light crosses the universe, it carries with it a time capsule. Photons don't just illuminate, they inform. Each one that reaches our eyes or telescopes has travelled across years, centuries, or even cosmic epochs. The further away the source, the older the light. When you look up at a star that's 1,000 light years away, you're seeing it as it was when medieval castles still echoed with the sound of armour and horseshoes. For stars within our own galaxy, these time gaps are manageable. Dozens, hundreds, maybe thousands of years. But when we peer deeper into other galaxies, we're talking millions or billions of years. Some of the most ancient light we've ever detected began its journey just a few 100 million years after the universe itself was born. Those photons have travelled the length and age of the cosmos to reach us, bringing stories from a time before our sun, before Earth, before any form of life we know. Light doesn't age or degrade the way sound does. A photon doesn't grow fuzzy with distance. It doesn't fray at the edges. What can happen, however, is redshift. As the universe expands, it stretches the space between things. That stretching affects light too, elongating its wavelengths as it travels through expanding space. Photons that began as ultraviolet or visible light arrive as infrared or even microwaves. Their colour changes, not because they've slowed down, but because space itself has stretched around them. This cosmological redshift is more than just a curiosity. It's one of the main ways we know the universe is expanding. By measuring how much a galaxy's light has shifted toward the red end of the spectrum, astronomers can estimate how far away it is and how fast it's moving away from us. The further the galaxy, the greater the redshift. It's like hearing the pitch of a siren drop as it drives away, only stretched across light and time. Now, despite all these obstacles and oddities, most photons complete their journey without issue. They glide through the vacuum, shaped only by the gravity they encounter, and the occasional cloud of gas or dust. Eventually some reach a detector, a telescope mirror, a satellite sensor, or perhaps your own eye during a peaceful moment under the night sky. And in that instant, the journey ends. A photon that may have travelled for eons finally meets its end, not with a bang, but with the tiniest of interactions. It might excite a molecule in your retina, or bounce onto a CCD chip in a telescope. That small encounter becomes an observation, a data point, a discovery, or perhaps just a quiet moment of beauty. This is how light moves through space, not in chaos but in graceful persistence, unwavering, timeless, uninterested in speed limits or obstacles. Whether it brushes against gravity, slips through dust, or flies for billions of years in solitude, its purpose is simple: to travel, to carry, to reveal. And in that journey, it becomes more than just light. It becomes our messenger across the cosmos, the thread that connects us to the stars. Long before humans understood what a photon was, or what stars were truly made of, there was just light, and the curiosity to figure out what on Earth, or perhaps what in the heavens, was going on with it. Light was one of the earliest mysteries. It warmed us, illuminated our way, and showed us the world. But for most of history, we didn't know what it was. Was it a substance, a wave, a particle, a divine glow? The journey to answering that question would eventually lead to one of the most powerful tools in all of astronomy: spectroscopy. And it all began, in many ways, with a prism and a rather curious apple enthusiast named Isaac Newton. In the 1670s, Newton performed an experiment that was both simple and revolutionary. He took a glass prism and passed a beam of sunlight through it, expecting to see perhaps a colourful glow, maybe even a rainbow if he was lucky. What he actually saw was far more structured, a continuous spread of colours arranged in a smooth gradient from red to violet. What had looked like ordinary white light was, in fact, a blend of many colours, all hidden within it, waiting to be separated. Newton had discovered that white light could be broken apart into a spectrum, not scattered randomly, but divided in a precise and orderly way. This was not just a party trick, it was a revelation. He concluded that light was composed of different rays, with different refrangibilities, or bending powers, and that each colour bent at a slightly different angle when it passed through the prism. Now, Newton wasn't just fiddling with glassware for fun, although one suspects he enjoyed it. He was laying the groundwork for centuries of discovery. By showing that white light is not pure but composed of many colours, he opened the door to asking a new question. What happens when light comes from other sources? What does the spectrum of a candle look like? Or a burning coal? Or a star? That question lingered in the air for over a century, until a German optician named Joseph von Fraunhofer picked it up in the early 1800s. Fraunhofer, who was an orphan and a self-taught genius in glassmaking, had a deep fascination with light and optics. In fact, the modern optical lens industry owes a lot to his work. But what truly set him apart was a peculiar discovery he made while analysing sunlight. Using a prism and a telescope, Fraunhofer passed sunlight through his setup and observed the resulting spectrum. Like Newton, he saw the familiar rainbow of colours. But unlike Newton, he noticed something odd. There were dark lines running through the spectrum. Tiny, sharp, precisely placed black lines, like scratches on a record. And they weren't random. They appeared in the same place every time he looked at the sun's light. Even more interesting, when he looked at the light from different sources like flames or artificial light, the lines changed. Some disappeared. Others appeared in new positions. Fraunhofer had stumbled upon one of the universe's secret languages, the absorption lines in the solar spectrum. Today, we call them Fraunhofer lines in his honour. He carefully mapped out hundreds of them with incredible precision, assigning each one a letter and measuring its position. He didn't know what caused them, but he knew they were real, reliable, and deeply significant. And he was absolutely right. Those dark lines were not flaws or optical quirks. They were the fingerprints of atoms absorbing specific wavelengths of light. When light passes through a cooler gas, atoms in the gas can absorb photons with exactly the right amount of energy to bump their electrons to higher energy levels. These absorbed wavelengths don't make it through, and they show up as dark lines in the spectrum. But Fraunhofer didn't yet know that. The physical explanation wouldn't come until decades later, when scientists began to connect the dots between chemistry and light. In the mid-19th century, two German scientists, Gustav Kirchhoff and Robert Bunsen, the very same Bunsen responsible for that famous burner in school labs, discovered that each chemical element, when heated, emitted light with a unique set of spectral lines. It was like each element had its own glowing barcode. By passing light from a flame through a prism and observing the resulting spectrum, they could identify which elements were present in the flame. Sodium, for example, produced a brilliant yellow line. Hydrogen had a whole series of lines in the red, blue, and violet. Suddenly, light became more than just illumination. It became information. Spectroscopy was born. Kirchhoff and Bunsen realized that those dark lines Fraunhofer had seen in sunlight matched the bright lines produced by heated elements. The implication was profound. The sun, and by extension all stars, contained the same elements found here on Earth. It was a moment of elegant symmetry. The cosmos was not made of something unknowable or alien. It was made of the same stuff, obeying the same laws. This was the start of modern astrophysics. With spectroscopy, astronomers could now analyze the light from stars, nebulae, and even galaxies, and determine their chemical composition, temperature, motion, and more. And it all came from understanding how light interacts with matter. Spectroscopy became the cosmic translator, the tool that allowed us to read the universe. It told us that stars are mostly hydrogen and helium, that some are moving toward us while others are drifting away, and that there are clouds of gas between us and distant galaxies. All of this from nothing more than a bit of light split into its components. It's worth pausing to appreciate how bizarre this is. With a prism or a diffraction grating, we can analyze a flicker of light from an object millions of light years away and deduce what it's made of. No need to send probes or collect samples. We can read a star's autobiography from its glow. And this technique didn't just stay in the lab, it expanded into the sky. Astronomers began to classify stars based on their spectra, leading to the famous OBAF-GKM sequence, a way to categorize stars by temperature and spectral characteristics. Spectroscopy helped us identify quasars, measure the redshift of galaxies, and even detect planets around other stars by watching how their light subtly shifts due to the Doppler effect. In many ways, the story of spectroscopy is the story of seeing more than what meets the eye. A rainbow becomes a roadmap, a beam of light becomes a conversation, and a dark line on a spectrum becomes a whisper from a faraway sun. It all began with a prism and a question: why does light behave this way? Newton gave us the first hints. Fraunhofer revealed its strange complexity. Kirchhoff and Bunsen unlocked its code. And since then, countless scientists have built on that legacy, turning simple curiosity into one of the most powerful scientific tools we've ever known. It's strange to think that something as ephemeral as light, so fleeting, so intangible, can carry so much meaning. Yet it does. Every star you've ever seen, every galaxy, every flicker in the sky, all of it speaks through light. And thanks to a bit of glass and a few brilliant minds, we've learned how to listen. If you could somehow zoom into a beam of starlight and look at its most detailed components, you wouldn't see just a blur of white. You'd find a pattern, a signature, made of thin, precise lines spread across the colours of the rainbow. Some of those lines are bright and vivid, others are dark and almost invisible, but they're not random. They're the cosmic fingerprints of the elements that make up stars, galaxies, gas clouds, and just about everything else in the universe. These lines tell stories, quietly, reliably, and with absolute honesty. To understand why, we have to shrink ourselves down mentally to the scale of the atom. Atoms are mostly empty space. In the centre is a nucleus made of protons and neutrons, and around it, electrons dance in defined energy levels. These levels aren't like little orbits in a mini-solar system, although they're often drawn that way. They're more like standing waves, regions where electrons are most likely to be found. And these electrons can't just hang out wherever they like. They're confined to specific energy states. It's a bit like being told you're only allowed to sit in row 3, seat 5, unless you're handed a very specific ticket that lets you jump to row 4. Now here's where light comes in. If a photon, the smallest packet of light, comes along and has just the right amount of energy, it can be absorbed by an electron. That energy bump causes the electron to leap to a higher energy level. But this only happens if the photon matches that energy difference exactly. Too little energy. No dice. Too much. It ignores the photon entirely. This selectiveness is the key to absorption lines. When light passes through a gas, like the outer layers of a star or a cloud of interstellar hydrogen, the atoms in that gas can absorb photons of very specific energies. The result is that those particular wavelengths go missing from the light spectrum, and when we pass that light through a spectroscope, we see dark lines, places where those photons have been plucked out. These are absorption lines. They're like little notches in the light, each one corresponding to a specific jump between electron energy levels in a particular element. And since each element has a unique set of allowed jumps, The pattern of lines it produces is also unique. You could think of it like a barcode at the supermarket. Every element has its own code, and the spectroscope is the scanner that reads it. Hydrogen, for instance, the most common element in the universe, has a wonderfully elegant and simple spectral fingerprint. When a hydrogen atom's electron jumps between energy levels, it emits or absorbs light at very specific wavelengths. In the visible part of the spectrum, these lines make up what's called the Balmer series. They show up as a handful of thin lines in red, blue-green, blue-violet, and violet. The most famous of these is the H-alpha line, a deep red line that appears at about 656 nanometers. It's commonly seen in emission nebulae, those glowing red clouds of gas where new stars are forming, that red colour. It's the hydrogen atoms lighting up like neon signs in deep space. But emission lines aren't the opposite of absorption lines. They're more like the other side of the same coin. When an excited electron falls back down to a lower energy level, it releases a photon with a very specific energy. That photon becomes part of the emitted light, and if we observe it, we see a bright line at that wavelength. The atom gives back the energy it took in, but in its own distinct way. Imagine a group of atoms being zapped with energy, maybe from heat or ultraviolet light. Their electrons jump to higher energy levels and then promptly fall back down, giving off photons. If we observe the light coming directly from that glowing gas, we see a series of bright emission lines, like a string of tiny fireworks across the spectrum. It's like hearing atoms sing their own notes, each one precisely in tune. Now, depending on the circumstances, you might see either emission or absorption lines. If you're looking at a hot glowing gas directly, say the gas is in a nebula or in a flame, you'll mostly see emission lines. If you're looking at a continuous light source shining through a cooler gas, like a star's hot core shining through its cooler atmosphere, you'll mostly see absorption lines. But the real magic happens when you realise you can use these lines to identify what's out there, even if it's impossibly far away. Look at the light from a distant star, and you'll find absorption lines that match the patterns of hydrogen, helium, calcium, iron, and many more. You don't need to scoop up star samples or fly a probe into a supernova. The light does the hard work for you. All you need is a good prism and a sharp eye. It gets better. Not only can these spectral lines tell you what elements are present, but also how much of them there is. The depth or intensity of the lines reveals the concentration of those elements in the star's atmosphere. Stronger lines usually mean more atoms absorbing or emitting at that wavelength. We can even determine a star's temperature this way, because the strength of certain lines changes with temperature. For instance, hydrogen's absorption lines are strongest in stars around 10,000 degrees Celsius, where the atoms are in just the right state to absorb light efficiently. And it doesn't stop at composition and temperature. Spectral lines can shift depending on motion. If a star is moving toward us, its lines shift slightly toward the blue end of the spectrum. If it's moving away, they shift toward the red. This is the Doppler effect in action, and it allows astronomers to measure stellar velocities with incredible precision. There's something deeply satisfying about the way it all fits together. From the microscopic scale of atoms and electrons to the vastness of galaxies and nebulae, it's all connected by light and its subtle, specific behaviours. Spectroscopy at its core is just reading that connection. And it's not just for stars. The technique works on anything that emits or absorbs light. Gas clouds, comets, planetary atmospheres, even exoplanets. When we look at the spectrum of a distant planet's atmosphere and see a faint absorption line from methane or water vapour, we're using the same principle that revealed hydrogen in a candle flame in a 19th century laboratory. It's a universal tool. Perhaps the most poetic thing about these spectral lines is their permanence. The universe may be chaotic, but the rules of atomic transitions are dependable. Hydrogen will always produce the same Balmer series. Sodium will always glow that sharp yellow. Helium will always dance in the violet. These patterns are written into the fabric of matter itself, and that consistency is what makes them so powerful. A single line, seen in a faint smudge of light from a distant galaxy, can tell you that hydrogen is there. Another might say there's oxygen. Another maybe nitrogen. Together they tell you the story of stars being born, burning bright and scattering their elements into space. It's hard not to feel a little awe at that. The universe doesn't speak in words, but it does speak in light. And in the fine details of that light, in those narrow, perfect spectral lines, it tells you what it's made of, how fast it's moving, how hot it is, and what stage of life it's in. These aren't just fingerprints. They're symphonies played by atoms, patterns etched into light by the smallest building blocks of matter. Each one is a message. Each one is a clue. And all of them together make the sky a little less mysterious and a lot more magical. At first glance, a star seems like a fairly mysterious object, a glowing sphere of gas floating millions or billions of kilometers away, unreachable, untouchable, and far too hot to poke at with even the longest scientific stick. And yet, oddly enough, we know an astonishing amount about what stars are made of. We know what elements swirl in their atmospheres, which gases dominate their cores, and how those elements change over time. We know this without bringing home a single sample. There's no need to bottle a bit of starlight or ship back a spoonful of solar plasma. Instead, we just look, or more accurately, we look at the light. Light is the star's autobiography. Not the glossy, ghost-written kind, but the raw, truthful version. And we've learned how to read it with incredible finesse. When you look at a star through a spectroscope, you're not just seeing a bright blur of light. You're seeing the result of countless atomic interactions in the star's outer layers, layers cooler than the core, but still energetic enough to write information into every passing photon. These outer layers are where light interacts with atoms that leave telltale signatures behind. What you get when you spread the light out is a pattern of dark lines, absorption lines. These are not smudges or glitches. Each one is an element tapping you gently on the shoulder and saying, "I'm here." Each element absorbs light at very specific wavelengths. Hydrogen, helium, iron, calcium, sodium, they all have unique absorption patterns. These patterns show up as dark bands or lines in the star's spectrum, and they're as reliable as fingerprints. Even if you're looking at a star thousands of light years away, the pattern holds. The wavelengths at which those lines appear don't change, unless the star is moving relative to us, which causes the entire spectrum to shift slightly. But the spacing, the relative positions, the overall structure of those lines stays the same, and that's the magic. This is how we determine what stars are made of. It's like piecing together a recipe by smelling the steam from the pot. Scientists match the absorption lines in a star's spectrum to those produced by known elements in the lab. If the lines match hydrogen's pattern, then hydrogen is present. If they match helium's, or oxygen's, or magnesium's, then those elements are present too. The process is called spectral analysis, and it is one of the most quietly powerful tools in science. It's remarkable how much detail this technique reveals. For example, the Sun, the star we know best, has a spectrum that tells us it's made mostly of hydrogen and helium, with traces of heavier elements like oxygen, carbon, nitrogen, iron, and a sprinkling of others. These heavier elements, though a small fraction of the Sun's mass, leave strong, clear fingerprints. In fact, calcium leaves one of the most prominent absorption lines in the solar spectrum. You can see it even with modest equipment. And here's a delightful twist of history. Helium, the second most abundant element in the universe, was discovered not on Earth, but in the Sun. In 1868, during a solar eclipse, astronomer Jules Janssen observed the spectrum of the Sun's chromosphere, the layer just above the visible surface. He noticed a bright yellow line that didn't match any known element on Earth. A few months later, British astronomer Norman Lockyer independently spotted the same line and proposed that it came from a new element. He named it helium, after Helios, the Greek god of the sun. That's right. An element we now use to float birthday balloons was first found floating in solar light. It wasn't until nearly 30 years later that helium was finally detected on Earth. trapped inside uranium ores. Until then, it existed only as a spectral ghost, seen in starlight, but not in substance. It remains the only element to be discovered in space before being found here at home. That discovery was more than a curious coincidence. It was a proof of concept. If light could reveal an element unknown on Earth, what else could it reveal? The answer, it turns out, is almost everything. Spectral analysis not only tells us which elements are present, but how much of each one. The depth and width of the absorption lines give us information about abundance. Deeper lines usually mean more atoms are absorbing light at that particular wavelength. There are complexities, of course. Temperature, pressure, and magnetic fields can all influence the appearance of spectral lines, but with careful modelling, these variables can be untangled. Using these methods, astronomers have mapped the chemical compositions of thousands of stars. They found stars rich in metals, stars poor in metals, stars with unusual ratios of elements, and stars whose composition suggests they were born in entirely different parts of the galaxy. Some of the oldest stars ever found contain almost no heavy elements, supporting the idea that the first stars were made almost entirely of hydrogen and helium. The heavier elements, like iron, silicon and nickel, had to be forged later in stellar cores and scattered by supernova explosions. Even stars in other galaxies can be analysed this way. Though their light is fainter and more distant, their spectra still carry the same information. Light from a galaxy millions of light years away can tell us what its stars are made of, how much gas surrounds them, and even what the intergalactic medium contains. And it doesn't stop with composition. Because of the way atoms interact with light, spectral lines can also reveal the temperature of a star, its pressure, magnetic activity and motion. For example, if a star is moving away from us, its spectral lines will shift toward the red part of the spectrum. If it's moving toward us, the lines shift toward blue. This redshift and blue shift is caused by the Doppler effect, the same principle that changes the pitch of a passing siren. By measuring the amount of shift, astronomers can calculate a star's velocity with surprising precision. But among all the elements we see in starlight, hydrogen remains the most dominant. It's the universe's original building block, forged in the first few minutes after the Big Bang. Its spectral lines are familiar and elegant, especially the Balmer series, which falls in the visible part of the spectrum. When hydrogen absorbs or emits light, it does so in a series of narrow lines spaced according to a mathematical pattern, a harmony of physics and beauty. And yet even something as simple as hydrogen can behave in complex ways depending on its environment. In very hot stars, hydrogen may be fully ionized, meaning its electrons have been stripped away. In cooler stars, the hydrogen lines might be more pronounced. In dense environments, collisions between particles can broaden the lines. Each variation tells a story. There's also something quietly philosophical about all of this. We've never visited another star. We can't scoop up a sample, hold it in our hands, or bring it back to a lab. And yet, we know what stars are made of. We know that our sun contains iron and oxygen and traces of lithium. We know that some stars are enriched in elements like carbon or barium, likely because they absorbed material from a companion star. We know that some stars have atmospheres containing rare earth elements, or that others are surrounded by clouds of expelled gas rich in nitrogen. All of this comes from studying the light. Just the light. No physical contact, no interstellar travel, no need for futuristic technology. Just the clever decoding of ancient photons. This ability to read starlight has transformed astronomy from a science of observation into one of diagnosis. We're no longer just cataloguing what we see in the sky. We're understanding it, parsing its chemistry, tracing its history. And it all rests on those spectral lines, thin, precise, and infinitely revealing. The next time you see a star, even just a faint twinkle overhead, it might look like nothing more than a distant pinprick of light. But within that light is a message, a list of ingredients, a chemical fingerprint. And with the right tools and enough curiosity we can read it, no matter how far away the star may be. Picture yourself standing on a quiet street as a fire truck approaches. At first, the siren sounds high-pitched, almost shrill, but as the truck speeds past and moves away, the pitch drops and grows lower, fading into the distance. That sudden shift in sound isn't a trick of your ears. It's a real physical effect known as the Doppler effect. And while it's easy to hear with sound waves, the same principle applies to light, giving us one of astronomy's most useful tools for measuring motion in the universe. The Doppler effect, at its heart, is all about movement. When a source of waves moves relative to an observer, those waves become compressed or stretched depending on the direction of travel. If the source is moving toward you, the waves are squished together, closer, shorter, and higher in frequency. If it's moving away, the waves are stretched out, longer, lower in frequency, and more spread apart. With sound, we hear this as a change in pitch. With light, we see it as a change in colour. Now, light travels in waves too, though we usually don't think of it that way. These electromagnetic waves have a frequency and a wavelength, and when something emitting light is moving, those waves experience the Doppler effect. When a star or galaxy moves toward us, the light waves it emits are compressed, shifting toward the blue end of the spectrum. This is called blue shift. When it moves away, the waves are stretched out, shifting toward the red end of the spectrum. This is redshift. The effect is subtle, especially for everyday objects because light travels incredibly fast, just under 300,000 kilometers per second. For an object to noticeably shift the color of its light, it has to be moving at a significant fraction of that speed. That's why you don't see your car's headlights turn red as you drive away from your garage. But in the vast expanse of space, where distances are immense and celestial bodies can travel at thousands of kilometers per second, the Doppler effect on light becomes measurable and very informative. Astronomers have long used this phenomenon to learn about the motion of stars, galaxies, and even entire clusters of galaxies. When we observe the spectrum of a star, we look at its absorption lines, the same unique fingerprints left by elements like hydrogen or calcium. If those lines appear exactly where we expect them to be, then the star isn't moving much relative to us. But if the lines are shifted slightly toward the red or blue end of the spectrum, that tells us the star is moving. The direction and amount of shift allow us to calculate how fast and in which direction it's travelling. It's a bit like listening to the universe hum and noticing when certain notes are a little sharp or a little flat. This technique is especially powerful because it doesn't require a visible change in position. Even if a star is too far away to show noticeable movement across the sky, its spectrum can reveal whether it's heading toward us or drifting away. That subtle shift in colour becomes a cosmic speedometer, and it works on more than just stars. We can use redshift and blue shift to measure the orbital motion of binary stars, those locked in a gravitational dance around one another. As one star moves toward us in its orbit and the other moves away, their spectral lines shift back and forth in a rhythmic pattern. This wobbling spectrum tells us not only that the stars are orbiting each other, but also their speeds, their masses, and even the shape of their orbits. It gets even better when applied to planets. When a star has a planet orbiting it, the planet's gravity causes the star to move in a tiny orbit of its own. The result is a minuscule Doppler shift in the star's light, a back and forth wobble that we can detect with extremely sensitive instruments. This is one of the main ways we discover exoplanets, worlds beyond our solar system. We don't see the planets directly, but we detect their presence by the way they tug on their stars, altering the colour of starlight in a whisper only careful ears, or rather, eyes, can hear. Now all of this is impressive enough, but where the Doppler effect truly shines is when we start looking beyond individual stars and out into the broader universe. In the early 20th century, astronomers began to notice something odd. When they measured the light from distant galaxies, the absorption lines in their spectra were consistently shifted toward the red. And not just a little red, they were very red. The farther away a galaxy was, the more its light was redshifted. This observation, made most famously by Edwin Hubble, changed everything. It led to the realization that the universe is expanding. Galaxies aren't just scattered randomly in space, they're moving away from us, and from each other, as if space itself is stretching like a cosmic balloon. But here's the twist. In this case, the redshift isn't caused by motion through space in the usual sense. Instead, it's the space between galaxies that's expanding. As that space stretches, it also stretches the wavelengths of the light travelling through it. This is called cosmological redshift, and it's slightly different from the classic Doppler effect. But the result is similar. Light shifts to longer, redder wavelengths as the universe expands. This idea forms the cornerstone of modern cosmology. It tells us that the universe had a beginning, and that it's still evolving. The redshift of distant galaxies isn't just a curiosity. It's the evidence that led to the Big Bang theory. And the further we look, the deeper into the past we see, and the more red-shifted the light becomes. Some galaxies are so distant, their light has been stretched into the infrared, or even the microwave part of the spectrum. To observe them, we need specialized instruments like the James Webb Space Telescope, which is designed to catch those long-lost reddened whispers from the early universe. Redshift also allows us to measure the rate at which the universe is expanding. This rate is called the Hubble constant, and determining its precise value has been one of astronomy's great quests. By comparing the distances of galaxies to their redshifts, astronomers can estimate how fast space is stretching. Interestingly, different methods of measuring the Hubble constant give slightly different answers, leading to what's known as the Hubble tension, an ongoing mystery that may point to new physics or subtle gaps in our understanding. Despite its challenges, redshift remains one of our clearest windows into the universe's behaviour on the grandest scales. It shows us not just that stars and galaxies move, but how they've been moving across time. It tells us that space itself is dynamic, not static. And it reveals that light is more than illumination. It's a tracer, a marker of motion and history. Even nearby galaxies show redshift. The Andromeda Galaxy, however, is a famous exception. Its spectral lines are blue-shifted, meaning it's moving toward us. In fact, Andromeda is on a collision course with the Milky Way. Don't panic. It won't happen for another 4 billion years or so, and the stars inside both galaxies are so spread out that most will pass right by each other. But the motion is real, and we know it thanks to the Doppler effect. And just for the record, our Sun moves too. Our entire solar system is orbiting the centre of the Milky Way at about 220 kilometers per second. That motion influences the Doppler shifts we measure, and astronomers carefully account for it when analysing starlight. Even Earth's rotation and orbit around the Sun produce tiny Doppler shifts that must be corrected for. It's like trying to measure the motion of distant ships while standing on a moving boat. Everything is in motion, and the math helps us untangle it. At first glance, it might seem odd that colour can tell us so much, but once you understand the connection between motion and wavelength, the universe starts to speak in more than just brightness. It starts to speak in tempo, in colour-coded signals that, when pieced together, form a map not just of where things are, but how they move. It's a quiet elegance, no great clamour, no drama, just the shifting of light, softly hinting at the grand ballet of galaxies, the dance of stars and the stretch of space itself, all hidden in the colour of the cosmos, and all revealed by understanding how motion leaves its mark on light. If you were to step outside on a clear night and look up at the stars, you might notice something curious. Not all stars shine the same shade of white. Some twinkle with a slight bluish tint, others lean toward a golden hue, and a few, if you're lucky and patient, might appear faintly red. It's not just your eyes playing tricks in the darkness. Those colours are real, and they tell us something very specific about the stars themselves, their temperature. Stars are not simply white-hot objects, they are black bodies, at least very good approximations of black bodies in physics terms. That means they radiate light across a continuous range of wavelengths, and the peak of that radiation depends on how hot the object is. The hotter it is, the shorter the wavelength at which it emits most strongly. This is why very hot stars look blue and cooler stars look red. It's a relationship called Wien's law, and it elegantly links colour to temperature. The human eye is pretty good at detecting subtle changes in hue even at night. A redder star like Betelgeuse in the shoulder of Orion is significantly cooler than a blue star like Rigel, which hangs in Orion's foot. Red stars might have surface temperatures around 3,000 degrees Celsius, while blue ones can reach temperatures of 30,000 degrees or more. That's a tenfold difference, and it shows up vividly in their light. Our own sun, which we often draw as yellow, actually emits light most strongly in the green part of the spectrum. But because it radiates across all visible wavelengths relatively evenly, we perceive it as white with a golden tint, especially when filtered through Earth's atmosphere. Astronomers have turned this colour-temperature relationship into a classification system, sorting stars by their spectra and grouping them according to surface temperature and spectral features. This system is known as the spectral classification, and it's one of the most useful organisational tools in astronomy. The spectral types are labelled with the letters O, B, A, F, G, K, and M. That sequence might seem random at first glance, and honestly it is. Historically, the original system was based on the strength of hydrogen lines, and was later rearranged as scientists understood more about stellar physics. But the current system works beautifully, running from the hottest stars to the coolest. To help remember the sequence, generations of astronomy students have relied on a charming mnemonic, "Oh, be a fine girl, kiss me." Or, if you prefer something a little more modern and inclusive, "Only boring astronomers find gratitude keeps motivating." You can make your own, anything to help the letters stick. O-type stars sit at the top of the temperature scale. These are the scorching blue giants, burning at temperatures above 30,000 degrees Celsius. They're massive, luminous, and short-lived, spending only a few million years on the main sequence before burning out or exploding. Their light is intense and filled with high-energy ultraviolet radiation. B-type stars are still very hot, typically between 10,000 and 30,000 degrees. They glow blue-white and are also relatively rare in the galaxy. These stars often show strong helium lines in their spectra and weaker hydrogen lines compared to cooler stars. A-type stars, slightly cooler, have temperatures between 7,000 and 10,000 degrees. They're often dazzlingly bright in the night sky and have some of the strongest hydrogen absorption lines. Sirius, the brightest star visible from Earth, is an A-type star. It shines with a white brilliance that's hard to miss, especially in the winter skies of the Northern Hemisphere. F-type stars range from about 6,000 to 7,500 degrees. Their light is white with a subtle hint of yellow. They show both hydrogen and metal lines in their spectra, and their atmospheres start to show more complex chemistry. Then there's the familiar G-type star. That's where our Sun fits in, with a surface temperature of around 5,500 degrees. G-type stars are common and stable, living long lives measured in billions of years. Their light leans toward a soft yellow-white, and their spectra include lines from metals like iron, calcium and magnesium, as well as the ever-present hydrogen. K-type stars are cooler still, around 3,500 to 5,000 degrees. These are orange stars, still bright, still capable of hosting planetary systems, but quieter, steadier. Many of them are older than our Sun, and burn their hydrogen fuel more slowly, giving them longer lifespans. And finally we reach M-type stars, the red dwarfs. These are the coolest stars in the main sequence, with surface temperatures around 3,000 degrees or less. They're small, dim, and incredibly common, by far the most numerous type of star in the galaxy. Though they're difficult to see with the naked eye due to their low luminosity, red dwarfs are thought to account for as much as 70% of all stars in the Milky Way. Despite their unassuming nature, red dwarfs are fascinating. Because of their slow fuel consumption and low mass, they can burn for trillions of years, far longer than the current age of the universe. That means none of them have had time to die yet. Every red dwarf that ever formed is still out there, glowing faintly in the dark. They're like the penny pinchers of the stellar world, efficient, frugal, and enduring. On the opposite end, the blue giants and O-type stars are the extravagant spenders. They blaze with incredible energy but live fast and die young, often ending their lives as supernovae or collapsing into neutron stars or black holes. Their brilliance is dazzling but fleeting. Colour and temperature also influence other properties of stars. Hotter stars tend to be more massive and more luminous, while cooler stars are generally smaller and dimmer. A blue star can outshine the sun by a factor of 100,000, while a red dwarf may emit only a fraction of the sun's light. But their longevity and stability make them strong candidates for hosting life-bearing planets, if life can handle the occasional flare. Spectral classification is not just a matter of temperature. It also involves looking at the star's absorption lines in detail. Those lines tell us about the star's atmosphere, surface gravity, and even chemical composition. The letters O through M are often followed by a number from 0 to 9, further refining the classification. For example, a G2 star, like the Sun, is slightly hotter than a G5 star, but cooler than a G0. This added granularity helps astronomers pinpoint where a star falls in the continuum. And beyond the main sequence, there are still more classifications. Giants, supergiants, white dwarfs, each with their own temperature ranges and spectral features. A red supergiant like Betelgeuse may be cooler than the Sun, but is so enormous that it outshines hundreds of thousands of smaller stars combined. A white dwarf, on the other hand, can be hotter than most main sequence stars, but so tiny and faint that it's barely visible without a telescope. Ultimately, the colour of a star is more than just decoration. It's a direct expression of physics. It tells us about the heat radiating from its surface, the processes unfolding in its core, and its place in the life cycle of stars. And with nothing more than a careful look at that colour and the spectrum behind it, we can understand a star's temperament and history. It's a quiet kind of brilliance, how light carries so much hidden meaning. The glow of a star isn't just something to wish upon or admire on a clear night. It's a data stream, a message from a nuclear furnace light years away, telling you exactly how hot it is and what it's made of. All you have to do is know how to listen, or rather, how to look. When it comes to the stars, there are two elements that steal the show. They are the original building blocks, the cosmic cornerstones, and the two most talkative characters in the periodic table's celestial gossip, hydrogen and helium. These lightweights may sit at the beginning of the element lineup, but they carry nearly all the mass in the visible universe, shaping the destiny of stars and galaxies with quiet but relentless persistence. Hydrogen, element number 1, is the simplest atom imaginable. 1 proton, 1 electron, that's it. No frills, no fluff. It's so basic, in fact, that it makes up about 75% of the ordinary matter in the universe. Not just in stars, but in interstellar clouds, gas giants, even in your body, in the form of water, fats, and proteins. Hydrogen is everywhere, and it's been around since nearly the very beginning. In the first few minutes after the Big Bang, the universe was a soup of fundamental particles, mostly protons, neutrons, and electrons. As things cooled down just enough, protons and neutrons started to pair up to form the nuclei of light elements. Hydrogen was the first to emerge, mostly as single protons that later captured electrons to become atoms. A small amount of helium formed as well, but hydrogen dominated, and it's been dominating ever since. Hydrogen's simplicity is part of its charm, but don't let that fool you. It plays a starring role in some of the universe's most dramatic processes. In the cores of stars, hydrogen becomes the fuel for nuclear fusion. When enough of it collects in one place, gravity begins to squeeze it inward. As the pressure rises, so does the temperature. Eventually, when the temperature in the core reaches around 10 million degrees Celsius, hydrogen atoms begin to fuse together to form helium. This is not just a gentle handshake between atoms. It's more like a crowd of over-caffeinated dancers crashing into one another at unimaginable speeds. When two hydrogen nuclei, protons, manage to slam together hard enough, one of them can transform into a neutron, forming a heavier particle called deuterium. This kicks off a chain reaction of collisions and transformations, ultimately producing helium, light, and a remarkable amount of energy. That energy is what keeps a star shining. Every second, our sun converts about 600 million tons of hydrogen into helium. It loses around 4 million tons of mass in the process, which gets turned into energy according to Einstein's famous equation, E equals mc squared. That may sound like a lot, but the sun is enormous, and this steady burn has been going on for over 4 billion years and will likely continue for another 5 billion. But hydrogen isn't just responsible for keeping stars lit. It is also incredibly revealing when it comes to understanding them. Because of its simple structure, hydrogen produces a very clear and informative set of spectral lines. The Balmer series, which appears in the visible spectrum, includes several distinct lines, most famously H-alpha, a deep red line at around 656 nanometers. This line is so prominent that it is used to identify star-forming regions, track solar activity, and observe emission nebulae glowing across the galaxy. Even in distant galaxies, H-alpha can be used to trace patterns of star formation. Where you see strong hydrogen emission, chances are you're looking at a nursery of young hot stars surrounded by clouds of gas they're heating and exciting. The hydrogen atoms in those clouds are being energized, their electrons leaping up to higher energy levels and then falling back down, releasing photons of very specific energies in the process. That signature red glow is like a neon sign saying, stars are being born here. Then there's the Lyman series, which lies in the ultraviolet part of the spectrum. It's harder to observe from Earth's surface due to atmospheric absorption, but it's crucial in the study of very distant galaxies in the early universe. Hydrogen's spectral lines serve as mile markers in the light of quasars, allowing astronomers to map the distribution of gas across billions of light years. Helium, element number 2, is hydrogen's cooler, slightly more reserved sibling. It has 2 protons, 2 neutrons, and 2 electrons when fully intact, and it's the second most abundant element in the universe, making up roughly 24% of the ordinary matter. Like hydrogen, helium was born in the early minutes of the universe, during a process known as Big Bang nucleosynthesis. Unlike heavier elements, which are forged in stars, helium was formed directly from the early chaos. Despite its abundance, helium was a bit of a mystery for a while. It was actually discovered in the Sun before it was found on Earth. In 1868, astronomers noticed a yellow spectral line in the solar spectrum that didn't correspond to any known element at the time. They named the mystery substance helium, after Helios, the Greek god of the sun. It wasn't until decades later that helium was identified in terrestrial rocks and gas deposits. Like hydrogen, helium also contributes to a star's spectrum, though its lines are trickier to spot. In hotter stars, especially those of spectral types O and B, helium's absorption lines are quite strong. In cooler stars, the lines fade since helium atoms are not easily excited at lower temperatures. Nevertheless, its presence is unmistakable in many places. In particular, helium plays a major role in the later stages of stellar evolution. As stars run low on hydrogen, their cores contract and heat up, eventually reaching the point where helium can begin to fuse. This process requires even more heat, around 100 million degrees Celsius, and produces carbon and oxygen, the building blocks of more complex matter. Helium fusion doesn't last nearly as long as hydrogen fusion, but it's essential for the creation of heavier elements and the eventual enrichment of the galaxy. It's fascinating how 2 of the lightest elements, simple, stable, and incredibly abundant, have such a powerful influence on the cosmos. Hydrogen is the starter fuel, the spark that ignites stars and keeps them glowing. Helium is the byproduct of that reaction, and later becomes fuel in its own right. Together they form a kind of stellar life cycle that plays out over billions of years. Their simplicity also makes them incredibly useful for astronomers. Hydrogen and helium don't clutter their spectra with too many lines. unlike heavier elements that can produce forests of overlapping features. Instead, these two give us clean, reliable markers. When we see hydrogen lines shift, we know something is moving. When helium lines appear in certain kinds of stars, we learn about temperature, age, and fusion processes. Even in places where stars have long since died, hydrogen and helium leave their marks. In planetary nebulae, those glowing shells of gas ejected by dying stars, you'll often find strong hydrogen-helium emission lines. In the remnants of supernova explosions, traces of these elements help reveal the progenitor star's original composition. In the atmospheres of white dwarfs and neutron stars, thin layers of hydrogen or helium float above incredibly dense cores, whispering remnants of what once was. On a more cosmic scale, the ratio of hydrogen to helium is one of the key observational tests for the Big Bang theory. Measurements of ancient gas clouds, combined with detailed simulations of the early universe, confirm that the current abundance of these two elements matches what we'd expect if the universe began as a hot, dense fireball nearly 14 billion years ago. It's an extraordinary alignment between theory and observation, all grounded in the behaviour of the simplest atoms. Hydrogen and helium may not be flashy. They're not the elements of life, or the ones used in jewellery, or the ones with exotic names like neodymium or technetium. But they are the quiet workhorses of the universe, making up almost everything we see, and much that we can't. They are the fuel and the flame, the whisper and the roar. From the first stars to the latest galaxies, from the glow of nebulae to the spectral lines etched in ancient starlight, hydrogen and helium are always there, always telling us something, and all we have to do is look at the light and listen. At the heart of every atom is a kind of miniature symphony. Invisible, silent, but full of structure and rhythm, it plays out in the behaviour of electrons as they dance around the nucleus. And like any good symphony, this atomic performance has notes, distinct, precise, and never out of tune. These notes come in the form of energy transitions, and when electrons move between energy levels, they create the spectral lines we see in starlight. One of the most elegant and useful of these patterns is known as the Balmer series. The Balmer series is a set of spectral lines produced when electrons in a hydrogen atom fall from higher energy levels down to the second energy level, or an equals 2. It's a kind of cosmic staircase, where each step downward gives off a photon of light. And because these jumps involve specific energy differences, the photons released always have specific wavelengths. Johann Balmer, a Swiss mathematician, discovered this pattern in the late 19th century. He wasn't a physicist by trade, but he had a knack for numbers and curiosity to spare. By analysing the known wavelengths of visible hydrogen lines, he found a simple mathematical formula that could predict them all, and even extrapolate new ones. It was an early moment in science where elegance and observation met in perfect harmony. The Balmer series lies within the visible part of the spectrum, which is partly why it's so famous. These are the hydrogen lines we can actually see. The most prominent is H-alpha, a deep red line around 656 nanometers. It's the line responsible for the red glow of many emission nebulae and one of the most useful features in astronomical spectroscopy. Then comes H-beta in the blue-green, H-gamma in blue-violet, and H-delta even further toward violet. As you move up the series, from transitions like n equals 3 to 2, then 4 to 2, then 5 to 2, the energy difference increases, the photons get shorter in wavelength, and the colours shift toward the ultraviolet. Eventually the lines grow so close together that they blend into a blur called the Balmer limit, beyond which individual lines can no longer be distinguished. This limit sits at around 364 nanometers. You can imagine the Balmer series like the keys on a piano, each one a distinct tone that follows a pattern. The lower keys, the bigger transitions, are spaced farther apart and resonate with deep, strong colours. As you climb higher, the keys get closer together, producing finer, higher-pitched notes that drift toward the edge of perception. But hydrogen doesn't only sing in the visible range. If you start looking in the ultraviolet or infrared, you'll find other spectral series that follow the same principle, electrons jumping between energy levels and releasing or absorbing photons. Each series is defined by the energy level the electron lands on. The Lyman series is the ultraviolet sibling of Balmer. In this case, electrons fall to the n's equals 1 level, the ground state of hydrogen. These jumps involve larger energy differences, so the resulting photons have higher energies and shorter wavelengths, all in the ultraviolet range. The Lyman alpha line, for instance, sits at about 121 nanometers and is critical in studying distant galaxies, quasars, and the intergalactic medium. While you can't see the Lyman series with your eyes, you can see its effects through telescopes equipped for ultraviolet observations. It's often used to trace hydrogen gas across the universe, especially in regions where stars have not yet formed. The light from distant quasars, for example, passes through intergalactic clouds of hydrogen, each one imprinting a Lyman absorption line on the spectrum. These repeated imprints create what's known as the Lyman alpha forest, a series of absorption lines that map the universe's structure on the larger scales. Then there's the Passion series, which lives in the infrared. This one happens when electrons fall to the n equals 3 level. These transitions involve smaller energy drops compared to the Balmer or Lyman series, so the emitted photons are lower in energy and longer in wavelength. Although we can't see these lines directly with our eyes, they're crucial for observing stars and nebulae hidden behind dust. Infrared light can slip through dusty regions that block visible light, making the Passion series a handy tool for peeking into otherwise obscured parts of the galaxy. There are even more series beyond these, the Brackett series, Fund series, and Humphrey series, named after physicists who extended this family of hydrogen transitions. Each one corresponds to electrons dropping into increasingly higher base levels, n equals 4, n equals 5, and so on. The farther up you go, the longer the wavelength of the resulting light, and the more the series moves into the infrared. All of these series come from the same atom, humble hydrogen. It's extraordinary how one proton and one electron can generate such a rich variety of light, spanning the entire electromagnetic spectrum. And the reason it works so perfectly is that electrons are picky. They don't absorb or emit just any amount of energy. They only jump between specific levels, each one quantized, like steps on a staircase or fixed notes on a musical scale. It's no wonder that the structure of these spectral lines inspired early physicists like Niels Bohr to develop quantum theory. The Bohr model of the atom, which introduced the idea of quantized electron orbits, was largely built around explaining the Balmer series. It showed that the electron in a hydrogen atom could only occupy certain energy levels, and that light was emitted or absorbed when the electron transitioned between them. In the real world, of course, atoms are even more complex than Bohr's model suggests. Electrons behave as both particles and waves, and the true nature of their energy levels is governed by the elegant but slightly mysterious rules of quantum mechanics. But the basic idea remains the same. The spectrum of hydrogen, and of every atom, is a map of how its electrons move. In the grand scheme of things, spectral lines are a kind of cosmic fingerprint. But perhaps a better metaphor is a musical signature. Each element plays its own tune, composed of light rather than sound. Hydrogen's tune is simple but rich, fundamental, and instantly recognizable. Other atoms add more complexity, more harmonics, but the clarity of hydrogen's pattern makes it invaluable to astronomers. Even in chaotic places like the center of a galaxy or the aftermath of a supernova, the hydrogen lines persist, unwavering and precise. They're reliable indicators of temperature, motion, density, and composition. They show up in emission and absorption, in stars and nebulae, in galaxies near and far. They're also incredibly important for studying the early universe. The Lyman alpha line in particular is used to locate the most distant galaxies ever observed. Because of the universe's expansion, the ultraviolet Lyman alpha line gets redshifted into the infrared, where it can be detected by instruments like the James Webb Space Telescope. That redshift acts like a cosmic clock, telling us how far back in time we're looking. In a way, each spectral series is a different mode of hydrogen's cosmic voice. The Balmer series speaks to our eyes, glowing in the reds and violets of young stars and nebulae. The Lyman series whispers in ultraviolet, echoing across ancient space. The Passion and Brackett series hum in the warmth of the infrared, revealing stars still wrapped in clouds of dust. And they all come from electrons leaping between levels, small movements that create grand results. These are not random jumps, they're precisely tuned, dictated by the fundamental structure of the atom. It's like the universe handed hydrogen a musical instrument and said, play something simple but eternal. Whether viewed through a telescope or modelled in a physics classroom, the spectral series of hydrogen are a reminder that the universe, at its most basic level, is not chaotic. It's ordered, predictable, and beautiful. From deep red glows to invisible ultraviolet pulses, the light emitted by hydrogen tells a story not just about atoms, but about stars, galaxies, and the unfolding history of space itself. And all of it comes from tiny perfect jumps in a single simple atom. Starlight carries secrets, but it doesn't hand them over easily. Those delicate photons have travelled across the vast dark of space, sometimes for millions or even billions of years, only to land gently on a mirror or a sensor here on Earth. The moment they arrive is precious, fleeting, and packed with information. But to truly understand what they're saying, we need a translator. That's where the tools of stellar spectroscopy come in. Imagine trying to understand a song by staring at the air around a violin. That's what raw starlight is like. It's beautiful, but without the right equipment, it's a mystery. Fortunately, astronomers have developed a suite of instruments designed to break that light down, to tease apart its colours and read the fine print written across the spectrum. It all starts with a telescope. Telescopes are the light buckets of astronomy. Their job is to collect as much light as possible and funnel it to where it can be analysed. The larger the telescope's mirror or lens, the more light it gathers, which means it can see fainter objects and pick up finer details. This is crucial for spectroscopy, because the more photons you collect, the clearer your spectrum will be. Ground-based observatories are scattered across the globe, often built on mountaintops where the air is thin and dry. These locations are chosen to reduce the blurring effects of Earth's atmosphere, which can distort or absorb certain wavelengths of light. Some of the most famous observatories include Mauna Kea in Hawaii, home to the Keck telescopes with their enormous 10-metre mirrors, and the European Southern Observatory's very large telescope in Chile, perched high in the Atacama Desert. But even at the best locations, Earth's atmosphere presents challenges. It absorbs ultraviolet and much of the infrared spectrum, and it creates turbulence that can smear out light. That's why space telescopes are such game changers. The Hubble Space Telescope, launched in 1990, gave us some of the sharpest views of the cosmos ever taken, and it did more than just take pretty pictures. It also carried a spectrograph that allowed scientists to analyse the light from stars, galaxies, and even planets in remarkable detail. More recently, the James Webb Space Telescope has taken that capability to a new level. Designed primarily for infrared observations, Webb can see through cosmic dust and detect redshifted light from the early universe. Its spectrometers allow scientists to study the atmospheres of exoplanets, measure the composition of distant galaxies, and observe the birthplaces of stars hidden behind veils of gas. No matter where it's located, on a mountain, floating in orbit, or parked in a distant solar orbit like Webb, every telescope designed for spectroscopy needs one essential component: a spectrometer. A spectrometer is the device that breaks incoming light into its component wavelengths, creating a spectrum. The most common tool used in a spectrometer is a diffraction grating. You can think of a grating like a very finely ruled surface, covered with thousands of tiny lines per millimeter, that bends light in different directions depending on its wavelength. When light passes through or reflects off this grating, it fans out into a rainbow, separating red from blue, blue from violet, and so on. This is similar in spirit to how a prism works, bending light of different colours at different angles. But gratings are far more precise and better suited to scientific instruments. They allow astronomers to spread out light over a detector, capturing a detailed fingerprint of whatever object the telescope is pointed at. Once the light is dispersed into a spectrum, it falls onto a detector, usually a charge-coupled device, or CCD, similar to what's inside a digital camera but much more sensitive. The detector records the brightness of light at each wavelength, creating a data-rich image that scientists can analyze. A key concept in spectroscopy is resolution. Spectral resolution refers to how finely the instrument can distinguish between wavelengths. A high-resolution spectrometer can separate lines that are very close together, revealing subtle details in the spectrum. This is especially useful when studying stars with complex chemical compositions, or when trying to detect the tiny shifts in spectral lines caused by motion, like the wobble of a star due to an orbiting planet. Low-resolution spectra, on the other hand, are better for observing faint objects, or getting a quick overview of an object's general characteristics. Both types of instruments have their place. High resolution is like zooming in on a painting to see the brush strokes, while low resolution gives you the whole scene in a glance. Another crucial aspect is calibration. You can't just point a telescope at a star, record its spectrum, and assume you've got accurate data. Spectrometers need to be calibrated to ensure their measurements are meaningful. This involves using known light sources, like lamps filled with specific gases that produce well-defined spectral lines. By comparing the observed lines with their known wavelengths, astronomers can adjust their instruments to compensate for any errors or drifts in measurement. Calibration also helps correct for instrumental effects, atmospheric interference, and even the movement of Earth itself. After all, we're spinning on our axis, orbiting the Sun, and wobbling slightly due to the gravitational pull of the Moon and planets. These motions can all introduce tiny shifts in the light we observe, and they have to be accounted for with careful corrections. One fascinating technique used in some spectrometers is cross-dispersion. This method separates light not just in one direction, like a typical rainbow, but in two. It allows astronomers to capture multiple spectral orders at once, increasing the amount of information gathered in a single observation. It's a bit like getting several rainbows from the same source, each one revealing a different aspect of the light's story. Spectroscopy doesn't just happen in the visible part of the spectrum. Instruments have been designed to work in ultraviolet, infrared, and even X-ray wavelengths. Each part of the spectrum provides different insights. Ultraviolet spectroscopy can reveal the high-energy processes around hot stars and quasars. Infrared spectroscopy peers through dust to examine cool stars, protoplanetary disks, and even molecules in space. X-ray spectroscopy dives into the violent hearts of supernova remnants, neutron stars, and black holes. In recent years, spectrographs have been miniaturized and made more portable. They're not just found on massive observatories anymore. Some universities and amateur astronomers now use compact spectrometers on small telescopes to study bright stars, variable stars, or even to detect the composition of meteors as they streak through the sky. The technology has become more accessible, and the excitement of unlocking the secrets of Starlight is now something people can experience from their backyard, given the right equipment and a clear night. The data produced by these instruments is vast and detailed. Astronomers use powerful software to analyze spectra, measure line strengths, calculate velocities, and model atmospheric conditions. It's a kind of forensic science on a cosmic scale, using the faintest clues embedded in light to reconstruct events that happened far away and long ago. One of the most beautiful aspects of all this is how it connects our everyday world to the distant universe. The same principles that explain the colours in a soap bubble or the spectrum of a neon sign also govern the light from exploding stars and distant galaxies. Spectroscopy bridges the gap between the mundane and the magnificent, using a single universal language: light. The tools we've built to read that light are marvels of human ingenuity. From the first prisms held up to sunlight to today's space-based observatories, with gold-coated mirrors and cryogenically cooled detectors, the journey has been extraordinary. And yet the goal remains the same: to understand what the universe is made of, how it moves, how it changes, and how everything, from atoms to galaxies, can be studied through the quiet, steady stream of starlight. Stars may look like they're just sitting still, calmly twinkling away in the night sky, but that serene appearance is only skin deep. In reality, stars are in constant motion, spinning, orbiting, drifting, wobbling, and sometimes dancing around invisible partners. They are not fixed ornaments pinned to a celestial dome. They are travellers, participants in the great galactic ballet. And although we can't feel these motions directly, we can see them through the language of light. Spectroscopy, our trusty tool for decoding starlight, turns out to be an excellent motion detector. Not only does it reveal what stars are made of and how hot they are, it also gives us clues about how they're moving. And the key to all of this is how motion affects light. One of the simplest forms of motion we can observe is something called radial velocity. This is the motion of a star directly along our line of sight, either toward us or away from us. Imagine standing in the middle of a road as a cyclist pedals straight toward you. You can't see if they're drifting to the left or right, but you can definitely tell they're coming your way. That's radial motion, and when stars move in this way, their spectral lines shift due to the Doppler effect. If a star is moving toward us, the light waves get compressed. This pushes the spectral lines slightly toward the blue end of the spectrum, what we call a blue shift. If the star is moving away, the waves get stretched out, shifting the lines toward the red end, a redshift. The amount of this shift is directly related to the star's velocity. Even tiny changes in position can be measured this way, with instruments so sensitive they can detect motion of just a few meters per second. This might sound like a subtle trick, but it's incredibly powerful. It's how we know that many stars are part of binary systems, orbiting unseen companions. It's how we first detected planets orbiting distant stars, by watching the star's light wobble ever so slightly as it responded to the tug of a planet's gravity. And it's how we discovered that galaxies are moving away from us, with more distant galaxies redshifted so much that they act as signposts for cosmic expansion. But stars don't only move in straight lines toward or away from us, they also move across the sky in a motion called proper motion. This is the sideways drift of a star across the celestial sphere as seen from Earth. It's a bit like watching an airplane move across the sky from horizon to horizon, rather than flying directly over your head. Proper motion is a slower, more gradual change, usually measured in arcseconds per year. That might not sound like much, just a tiny sliver of a degree, but over time it adds up. Barnard's star, one of our closest neighbours, has the fastest known proper motion, shifting by over 10 arcseconds per year. That's still tiny to the naked eye, but it's lightning fast by astronomical standards. To measure proper motion, astronomers take very precise images of stars years apart and compare their positions. But proper motion is just the apparent motion on the sky. To understand the true space motion of a star, we need to combine both proper motion and radial velocity. One tells us how the star moves across our field of view, the other tells us how it moves toward or away from us. Together, they give a full three-dimensional picture of the star's motion through space. There's more though. Spectroscopy doesn't just tell us if a star is moving in a straight line, it can also tell us if it's spinning. When a star rotates, different parts of its surface are moving in different directions. The side rotating toward us is moving slightly closer, so the light from that side gets blue shifted. The side rotating away is moving slightly farther, so its light gets red shifted. The result is a kind of stretching of the star's spectral lines. they broaden out, smearing from sharp, narrow lines into fatter, fuzzier ones. This effect, called rotational broadening, is subtle but measurable. By analysing how much the lines are broadened, astronomers can estimate how fast the star is spinning. Some stars rotate leisurely, taking weeks to complete a single spin. Others, particularly young and massive stars, spin at dizzying speeds, sometimes hundreds of kilometers per second at the equator. Rapid rotation can even distort a star's shape. Instead of being perfect spheres, fast rotators can bulge at the equator and flatten at the poles, turning into what's known as oblate spheroids. This distortion affects the temperature and brightness across the star's surface. Its poles may be hotter and brighter than its equator, in a phenomenon called gravity darkening. Again, light is the messenger, and spectroscopy is the translator. Stars in binary systems provide another fascinating case study in motion. When two stars orbit each other, their mutual gravity causes them to wobble around a shared centre of mass. If we observe the system edge on, we can detect this wobble as periodic shifts in the spectral lines. First one direction, then the other, like a pendulum. These systems are known as spectroscopic binaries, and they're incredibly common. In some cases, we can see spectral lines from both stars. This is called a double-line spectroscopic binary. The lines from each star shift back and forth in opposite directions, like two dance partners circling each other. In other cases, we only see the lines from one star shifting, a single-lined spectroscopic binary, because the companion might be too faint or too small to contribute visible light, but its gravitational tug gives it away. These tiny motions can also reveal something even more elusive: the presence of exoplanets. When a star has one or more planets orbiting it, it doesn't sit still. It responds to the gravitational pull of those planets by moving in a tiny circular path. This creates a very subtle doppler shift in the star's spectrum, often just a few meters per second, but it's enough to be detected. This method, known as radial velocity detection, was one of the first ways we discovered planets beyond our solar system. By measuring how a star's spectral lines drift over time, we can infer the presence of a planet, estimate its mass, and even get a sense of its orbital period. It's like watching a tugboat bob in the water and inferring the presence of a small but persistent current. There are also other factors that can change the shape and position of spectral lines. Pulsating stars, for example, expand and contract rhythmically, which affects their surface velocities and produces periodic changes in their light. These pulsations can create subtle patterns in spectral data, revealing the internal physics of the star, a technique known as astroseismology. Some stars have stellar winds, streams of particles flowing away from the surface, which can produce asymmetries in spectral lines. Others experience flares, magnetic activity, or convection currents that stir the outer layers and affect the spectrum in more chaotic ways. Each motion leaves its fingerprint on the light. Even the sun is not exempt. Our own star oscillates, rotates, and shifts ever so slightly, and solar spectroscopists study these motions to learn about its interior structure. Using Doppler shifts across the solar surface, scientists can track convection cells, sunspot movements, and the rotation rate at different latitudes. In the end, what seems like a quiet, steady point of light is actually bursting with motion and activity. Stars wobble, spin, pulse, and orbit. They drift through space, rotate on their axes, and sometimes gallop through the galaxy in high-speed arcs. And all of it can be seen, measured, and understood through the spectrum of their light. Spectroscopy turns starlight into a kind of celestial dance chart. It doesn't just tell us what stars are, it tells us what they're doing. The gentle shift of a spectral line, the broadening of a feature, the rhythmic pulse in a data graph. These are the footprints of motion written in light. They are the whispers of stars in motion, echoing through time and across space, waiting patiently to be read. Imagine looking up at a star hundreds of light years away and somehow knowing that a tiny planet is circling it. Not because you've seen the planet directly, most are far too small and faint for that, but because of the slightest, most delicate changes in the star's light. It's like noticing a moth passing in front of a floodlight from across a football field. But astronomers have found a way to do just that, and with the help of light, they've discovered thousands of distant worlds orbiting stars beyond our own solar system. These are exoplanets, or extrasolar planets, planets that live in solar systems other than our own. And while they were once the stuff of science fiction, they've now become one of the most vibrant fields in astronomy. Today we know of over 5,000 confirmed exoplanets, and each one tells us something new about what's possible in the universe. So how do we find them? How can a planet which doesn't emit its own light give itself away from such an enormous distance? The answer, as always, lies in starlight. One of the most effective techniques is called the transit method, and it's surprisingly intuitive. Picture a star as a big glowing disk. If a planet happens to pass directly between that star and our vantage point here on Earth, it blocks a tiny bit of the starlight. Just a sliver, but that sliver can be measured. The effect is called a transit, and it causes a temporary dip in the brightness of the star. The dip is small, usually less than 1% of the total light, but if it happens repeatedly, at regular intervals, and with a consistent pattern, it's a strong sign that a planet is orbiting the star. It's like watching a clock with a glitch in the glow. Every few days or weeks there's a brief flicker, a soft shadow that appears and disappears, and if it keeps happening with a steady rhythm, you can start to infer the properties of whatever's causing the eclipse. From the depth and shape of the dip in light, astronomers can calculate the size of the planet and the length of its orbit. A shallow dip might mean a small rocky planet like Earth. A deeper dip could indicate a larger gas giant like Jupiter, and if the transit lasts longer, the planet may be farther from its star, taking more time to cross. The beauty of the transit method is that it doesn't require any complex imaging of the planet itself. All it needs is a reliable stream of starlight and a very sensitive detector. Space telescopes like Kepler and TS have used this method to great effect, monitoring hundreds of thousands of stars and watching for those subtle telltale dips. But the transit method has its limitations. It only works if the planet's orbit is aligned just right, so that it passes between us and the star. If the orbit is tilted even slightly, we might miss the transit entirely. That's why the method works best when applied to large numbers of stars, casting a wide net in hopes that some planetary systems happen to be edge-on from our perspective. To complement the transit method, astronomers also use another powerful technique, the radial velocity method, sometimes called doppler spectroscopy. This method relies not on the dimming of starlight, but on its shifting. As a planet orbits a star, it doesn't just move in a neat circle while the star stays still. Both objects actually orbit a common centre of mass. For a massive star and a small planet, the centre is located very close to the star's centre, but not exactly at it. That means the star moves too. Just a little, wobbling back and forth in response to the planet's gravitational tug. This motion affects the star's light. When the star moves toward us, its spectral lines shift slightly toward the blue. When it moves away, they shift toward the red. This is the Doppler effect at work, and by measuring these tiny shifts, astronomers can detect the wobble caused by an orbiting planet. The changes are incredibly subtle, sometimes just a few meters per second, but they're enough to produce a measurable shift in the position of absorption lines in the star's spectrum. These shifts create a sinusoidal pattern over time, like a smooth wave rising and falling, each peak and trough marking a point in the star's orbit. From this wave, astronomers can calculate the mass of the planet and how far it is from its star. Unlike the transit method, radial velocity doesn't require the planet to pass in front of the star. It works as long as there's a detectable wobble, making it useful for discovering planets in a wider range of orbits. Combining both methods can be particularly powerful. If a planet is detected by both transit and radial velocity, we get a wealth of information. The transit gives us the planet's size, while the radial velocity gives us its mass. Together these allow us to calculate its density, which tells us whether it's a rocky terrestrial world, a gas giant, or something in between. This is how we've discovered some truly remarkable worlds. Hot Jupiters that orbit their stars in just a few days, super-Earths with twice the mass of our own planet, and even planets in the habitable zone, the region where temperatures might allow liquid water to exist. And as instruments improve, we're beginning to study the atmospheres of exoplanets too. During a transit, a tiny fraction of the star's light filters through the planet's atmosphere before reaching us. That light picks up spectral fingerprints of the gases in the atmosphere, revealing their composition. This method, called transmission spectroscopy, has already allowed scientists to detect elements like sodium, potassium, and water vapor in exoplanet atmospheres. In some cases, there are hints of carbon dioxide, methane, or other organic molecules. These detections are preliminary, but they're incredibly exciting. They open the door to the search for biosignatures, chemical signs of life. Space telescopes like Hubble and James Webb are equipped with the tools to perform this kind of atmospheric analysis. Webb in particular was designed with exoplanets in mind. Its infrared capabilities allow it to peer into the hazy atmospheres of distant worlds and detect the faintest traces of chemical signatures. All of this, planet sizes, orbits, masses, compositions, comes not from photographing the planets themselves, but from reading the changes in a star's light. It's a game of cosmic inference, built on careful observation and patient decoding, and light, once again, is the hero of the story. There are other methods too, each with its own strengths. Gravitational microlensing can detect planets when a foreground star temporarily magnifies the light of a background star. Direct imaging, while challenging, has succeeded in capturing the faint glow of young, hot planets far from their host stars. Astrometry, which measures precise changes in a star's position, may eventually add more discoveries to the growing list, but time and again, it's the subtle changes in starlight that reveal the most. A dip here, a wobble there, a spectral line that slides ever so slightly. From those faint signals, we piece together planetary systems light years away. Perhaps the most profound part of this journey is what it implies. If our Sun is just one star among billions, and if exoplanets are common rather than rare, then the universe is likely teeming with worlds. Icy ones, fiery ones, gaseous giants, rocky twins, and maybe, just maybe, life-bearing planets, not so different from our own. And we're finding them not with starships or landers, but with photons, with the quiet, steady stream of light that travels across the void, carrying secrets and signatures, waiting patiently to be understood. A planet may cast only the faintest shadow on its star, or tug ever so gently at its light, but for those who know how to read it, that's more than enough. If you could rewind the universe back to its earliest moments, before the galaxies, before the stars, before anything remotely resembling a planet, what you'd find is a vast expanding sea of incredibly hot, incredibly simple matter. Just minutes after the Big Bang, the universe was filled with a scorching soup of fundamental particles zipping around at nearly the speed of light. There were no complex atoms, no heavy elements, just the lightest ingredients, hydrogen and helium, with a whisper of lithium. It was by all standards a chemically boring universe. But what followed was nothing short of cosmic alchemy. Over billions of years, the universe turned that bland hydrogen and helium mixture into a rich periodic table of elements: carbon for life, oxygen for water, iron for blood and skyscrapers, silicon for sand and circuits. And astonishingly, we know this entire transformation happened not because we've flown to distant galaxies or scooped up samples from ancient stars, but because of light. Starlight, filtered through the lens of spectroscopy, tells the whole story of how the universe built its own complexity, one atom at a time. The tale begins with gravity. Over time, tiny fluctuations in the density of the early universe allowed clouds of hydrogen and helium to collapse. As they did, they formed the first stars, massive, hot and short-lived. These were likely what we call population 3 stars, theoretical, metal-free stars made almost entirely of hydrogen and helium. We've never observed them directly, but their existence is inferred from the chemical signatures we don't see in the oldest known stars. These first stars were the universe's original fusion reactors. Inside their cores, hydrogen atoms were fused into helium, and in the most massive among them, the fusion continued. Helium into carbon, carbon into oxygen, oxygen into neon, and eventually into silicon and iron. Each stage released energy, fueling the star and fighting against the inward pull of gravity. But once a star starts making iron, the story changes. Iron is a dead end, energetically speaking. Fusing iron doesn't release energy, it costs it. When iron builds up in the core, the star runs out of fuel and collapses under its own weight. This collapse happens fast, catastrophically fast. In a matter of seconds, the core implodes, rebounds, and triggers a massive explosion, a supernova, and it's in these fiery death throes that some of the most precious elements in the universe are forged. Gold, uranium, lead, and other heavy elements are created in the chaotic burst of nuclear reactions that occur during these explosions. The star, once a giant furnace, becomes a chemical fireworks show, scattering newly forged elements out into the cosmos. These enriched gases don't just drift aimlessly. Over time, they mix with surrounding hydrogen and helium, seeding the interstellar medium with heavier elements. When new stars form from these clouds, they inherit some of that material. These second-generation stars, known as population 2 stars, have trace amounts of elements like carbon, nitrogen, and oxygen. Tiny signatures that tell us they were born into a universe that had already started its chemical transformation. And so the cycle continues. Stars live, burn, and die, returning their matter to space. New stars and planets form from that recycled material, enriched a little more each time. This process of stellar birth, fusion, death, and rebirth is how the universe went from a sparse cloud of simple atoms to one filled with galaxies, complex chemistry, and the building blocks of life. Spectroscopy lets us trace this entire journey. When we analyse the light from a star, we're not just seeing how hot it is or how fast it's moving, we're seeing what it's made of. Every element in a star's atmosphere leaves behind a unique fingerprint in the spectrum, those absorption lines that tell us, for instance, whether there's calcium or sodium, iron or oxygen. And because we can measure these elements precisely, we can determine how metal-rich a star is. In astronomy, the term metals includes every element heavier than helium. It's a bit of a simplification. Oxygen and carbon aren't metals in the traditional sense, but it helps distinguish between the primordial elements and those created later. A star's metallicity, or metal content, acts like a cosmic birth certificate. High metallicity means the star formed in a universe that had already gone through many cycles of star formation and death. Low metallicity suggests a more ancient origin. The oldest stars we've found, often located in the halo of our galaxy, or in ancient globular clusters, have extremely low metallicities. Some contain only 1 part in 100,000 of heavy elements compared to the Sun. Their light, studied carefully through spectroscopy, reveals a nearly pristine composition, mostly hydrogen and helium, with just a trace of later ingredients. These stars are like fossils, preserving the chemistry of the early universe. By mapping metallicity across the galaxy, astronomers can build a timeline of stellar populations and chemical evolution. Younger stars, especially those in the galactic disk, tend to be more metal-rich. Older stars in the halo or bulge are generally poorer in metals. This gradient tells us how the galaxy assembled itself over billions of years from the inside out. And this isn't limited to our own galaxy. Spectroscopy allows us to study the chemical composition of stars in nearby galaxies too. We can measure the metallicity of stars in the Magellanic Clouds, the Andromeda Galaxy, and even in more distant systems. We see how different galaxies evolve at different rates, some building up their heavy elements quickly, others slowly. Even the gas between stars speaks to us through light. Spectroscopy of distant quasars, bright active galactic nuclei powered by supermassive black holes, often reveals absorption lines from intervening clouds of gas. These clouds, sometimes billions of light years away, leave narrow fingerprints in the light as it passes through them. By studying these lines, we can measure how the chemical composition of the universe has changed over time. What emerges from all this is a picture of a universe in chemical flux. Once composed almost entirely of hydrogen and helium, it has slowly enriched itself through countless cycles of stellar life and death. Elements needed for life, carbon, nitrogen, oxygen, phosphorus, sulfur, were forged in stars and scattered into the cosmos. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it came from stars. We are quite literally stardust. And we know this not because we've gathered samples from across the galaxy, but because of light. The light from stars and galaxies carries with it the imprint of the elements they contain. Spectroscopy gives us the tools to decode that imprint, to read the history of cosmic chemistry written across the sky. It's astonishing, really. With just a beam of starlight split through a prism or grating, we can peer back billions of years and watch the universe build itself, atom by atom. Every spectral line is a message from the past, a glowing trace of fusion, explosion and transformation. So the next time you look at a star, any star, whether brilliant and blue or faint and red, you're not just seeing a point of light, you're seeing the product of cosmic recycling, the ongoing story of how hydrogen became helium, how helium became carbon, and how eventually a universe that began with simplicity learned how to make complexity. And it's still happening. New stars are being born, old stars are dying, the universe is still writing its chemical story, quietly, slowly, and always in light. If you were to look up at the night sky and somehow peel back all the stars, you'd find something even grander behind them. Galaxies. Not just a handful or a few dozen, but billions of them. Each one is a sprawling collection of stars, gas, dust, dark matter and mystery. Some are neat and spiral-shaped, others are rounded and smooth, and a few look like someone shook the cosmos and left the pieces scattered. They're beautiful, complex, and very far away. But even from across billions of light years, galaxies still whisper their secrets to us, through light. Galaxies may seem too distant or too large to analyse in the same way we study stars, but the truth is we can learn just as much, sometimes even more, by studying their light. When we spread that light out into a spectrum, it becomes a treasure map of information, revealing not just what the galaxy contains, but what it's doing, how fast it's changing, and how far back in time we're seeing it. To begin with, let's talk about what we see when we look at a galaxy. With the naked eye, most galaxies are faint smudges, if we can see them at all. The Andromeda Galaxy, for instance, is just barely visible under very dark skies. But with a telescope, that smudge transforms into structure. Spiral arms, glowing cores, filaments of dust. What you're seeing is the combined light of hundreds of billions of stars, all packed into a gravitational embrace. Now, just like with individual stars, that light contains layers of meaning. When we take the spectrum of a galaxy, we're essentially gathering the blended light of everything inside it. Stars, gas clouds, nebulae, and sometimes even supermassive black holes. And remarkably, we can separate those ingredients. It's a bit like tasting a complex soup and being able to pick out the garlic, the basil, the tomatoes, and the pinch of pepper just by paying attention. The first clue a galaxy gives us is its type. Galaxies come in several general flavours: spiral, elliptical, irregular, and lenticular. Spiral galaxies, like the Milky Way and Andromeda, are full of gas, dust, and active star formation. They have young blue stars lighting up their arms, and often a central bulge of older, redder stars. Elliptical galaxies, on the other hand, are more like giant space potatoes, smoother, rounder, and generally redder. They've used up much of their gas and don't form many new stars. Most of their light comes from older, cooler stellar populations. By analysing a galaxy's colour and spectrum, we can tell what kinds of stars dominate it. Blue-dominated light suggests ongoing star formation and younger stars. Redder light usually means an older, quieter galaxy. And somewhere in between, we find galaxies that are transitioning. Maybe they've just finished a burst of star formation, or maybe they're running low on gas. Speaking of gas, spectroscopy also tells us a lot about the interstellar medium in galaxies. Gas doesn't just sit there quietly, it glows. In regions where stars are forming, young hot stars pump out ultraviolet light that excites nearby hydrogen atoms. These atoms then emit light as they cool down, especially in the hydrogen alpha line at 656 nanometers, a deep red signature that astronomers use to trace star-forming regions. When we observe a galaxy in H-alpha, we can map out where new stars are being born. These glowing regions often cluster along the spiral arms, where gas is densest. In some galaxies, the entire disk is lit up with star formation. In others, starbirth is confined to a central ring or spread out in knots and filaments. And in still others, like many elliptical galaxies, the H-alpha signal is almost completely absent. Other spectral lines reveal the presence of heavier elements like oxygen, nitrogen, and sulfur. By comparing the strength of these lines, we can estimate the metallicity of a galaxy, that is, how chemically enriched it is. Galaxies with lots of star formation tend to have more metals, since stars create these elements and spread them through the interstellar medium. This enrichment process is part of a galaxy's ongoing evolution, and by looking at galaxies of different ages and distances, we can actually track how the universe has changed chemically over time. Now let's take that light and stretch it across space. The farther a galaxy is, the more its light is redshifted, stretched out as the universe expands. This redshift not only tells us how far away the galaxy is, it also tells us how long ago the light was emitted. When we look at a galaxy that's 5 billion light-years away, we're seeing it as it was 5 billion years ago. Its light has travelled all that time just to reach us, carrying a snapshot of what it looked like before Earth even had fish. Galaxies at different redshifts show different stages of development. Nearby galaxies are often well formed, with clear structures and settled populations of stars. But as we look farther back, we start to see galaxies in the midst of their growth. Irregular shapes, wild star formation, and chaotic mergers. These are the baby pictures of the universe, and they show us how structure formed and evolved. And then there are the dramatic ones, the galaxies that light up like cosmic fireworks. These often contain active galactic nuclei, or AGNS. At the heart of almost every large galaxy is a supermassive black hole. Most of the time, these black holes are quiet, but in some galaxies, gas and dust fall into them at such high speeds that the material heats up and emits huge amounts of energy. The result is a luminous, energetic core that can outshine the rest of the galaxy combined. AGNs come in many forms: quasars, blazars, Seyfert galaxies. Their spectra are unmistakable, broad, intense emission lines, often from highly ionized elements, and sometimes features like jets or radio lobes. Quasars, in particular, are some of the brightest objects in the universe, visible from billions of light-years away, and all of their secrets, mass, spin, rate of feeding, are hidden in their light. Spectroscopy helps us untangle that light. We can measure the width of spectral lines to estimate the speed of gas orbiting the black hole. We can detect elements that have been blasted into high-energy states. We can even map how the light varies over time, revealing turbulence and motion in the accretion disk. Even galaxies that aren't active still have movement within them. Using the Doppler effect, astronomers can measure how stars and gas are moving inside a galaxy. Light from one side of a rotating galaxy will be blue-shifted as it moves toward us. while light from the other side is redshifted as it moves away. This allows us to map a galaxy's rotation curve, and surprisingly, that's where one of astronomy's biggest mysteries comes from. When we chart these curves, we find that stars at the outer edges of galaxies are moving far faster than expected, faster than gravity from the visible matter alone should allow. This discrepancy is one of the main pieces of evidence for dark matter, the unseen material that appears to make up most of the mass in the universe. Once again, it's light, not direct observation, that brings this invisible force to our attention. The more we study starlight from galaxies, the more layers of meaning we uncover. It tells us how galaxies live, how they grow, and how they sometimes collide and merge. It reveals bursts of star formation, quiescent periods of aging, and the tumultuous influence of black holes. And the distances involved are staggering. Some of the galaxies we've studied in detail are over 10 billion light-years away. Their light began its journey when the universe was still a toddler, yet here it is, arriving in our detectors, carrying all the information we need to learn about those ancient times. Galaxies may be faraway cities of stars, but their light is immediate. It falls on our telescopes, flows into our spectrometers, and prints its story in fine spectral lines. We don't need to travel to those galaxies to understand them. We just need to pay close attention to what their light is saying. And in the silence of space, that light never stops speaking. There's something deeply poetic about the way a star ends its life. After millions or even billions of years of steady burning, fusing, glowing, radiating gently into the cosmos, it doesn't simply fade away. Some stars go out with a bang so powerful it can outshine an entire galaxy for weeks. A supernova is not just a dramatic finale. It's an explosion so energetic that it shakes the very fabric of space, tears atoms apart, builds new ones, and launches them across the galaxy at thousands of kilometers per second. And, as always, the key to understanding it all is light. When a star explodes, its light doesn't simply flick on and off like a bulb. The brightness rises sharply, then slowly fades over days, weeks, or even months. But if you look beyond the glow, beyond the sheer intensity, and break that light into a spectrum, what you'll see is something even more astonishing. A story unfolding in colour and line, a moment-by-moment record of nuclear chaos, elemental creation, and cosmic recycling. Supernovae come in several types, but the two most well-known are Type 1 and Type 2. Each has its own signature, both in behaviour and in its spectrum. Type 2 supernovae occur when a massive star, at least 8 times the mass of our Sun, reaches the end of its fuel supply. The core collapses, gravity wins the battle, and the result is a catastrophic explosion. Hydrogen features prominently in these spectra since the outer layers of the star still contain large amounts of it. In contrast, Type 1 supernovae, specifically Type OID, don't come from single massive stars, but from white dwarfs in binary systems. A white dwarf can steal matter from its companion star until it reaches a critical mass, about 1.4 times the mass of the Sun. At that point, it can no longer support itself, and it undergoes a thermonuclear explosion. These explosions tend to show little or no hydrogen in their spectra, but they do exhibit strong silicon lines early on. The difference matters because the type of supernova tells us not only how the explosion happened, but also what elements are likely to be produced and ejected into space. And we figure all of this out not from the brightness alone, but from the way the spectral lines behave before, during, and after the blast. When a supernova first erupts, it reaches its peak brightness in a matter of days. The early spectrum is dominated by broad absorption lines caused by rapidly expanding material. These lines aren't sharp and well-defined like you might see in the spectrum of a stable star. They're smeared out, broadened, due to the high speeds involved. The outer layers of a supernova can expand at tens of thousands of kilometers per second, which stretches the light into a wide, shallow trough in the spectrum. That broadening tells us just how fast the material is moving. For Type 2 supernova, One of the most striking features early on is the hydrogen alpha line. It's the same deep red line we see in nebulae and star-forming regions, but here it's broadened and distorted by the extreme dynamics of the explosion. As the blast progresses, the hydrogen lines evolve and new elements start to appear. In T-Pei supernovae, the early spectra often show strong lines of singly ionized silicon, a reliable fingerprint used to identify this specific type. The presence of silicon, along with the absence of hydrogen, is a dead giveaway that we're looking at a white dwarf explosion. Over time, as the supernova cools and the outer layers thin out, lines from iron, nickel and cobalt emerge, elements formed in the heart of the detonation. These heavier elements aren't just floating around in the outer atmosphere of the star, they're being forged in real time through a process called nucleosynthesis. During the explosion, temperatures rise so high, into the billions of degrees, that atomic nuclei are smashed together, building new elements atom by atom. The very iron in your blood and the calcium in your bones were likely created this way, in some ancient supernova that exploded long before Earth existed. By taking spectra at different times during the supernova's evolution, astronomers can build a kind of chemical timeline. Early on, the light is dominated by the surface material, hydrogen, helium, or whatever made up the star's outer layers. As time passes, deeper layers become visible, and new lines begin to dominate. You can see the transition from silicon and sulfur to iron and cobalt. Each element appears at a different phase, like actors entering the stage on cue, each one playing a crucial role in the grand finale. And then there's the nebula phase. After the supernova has faded from its blinding peak and the material has expanded into space, the spectrum changes again. The light now comes from glowing gas, heated by radioactive decay. In particular, the decay of nickel-56 into cobalt-56 and then into iron-56 provides energy that keeps the remnant glowing long after the explosion has passed. During this phase, emission lines become more prominent. Unlike the earlier absorption-dominated spectra, nebula spectra are filled with narrow, sharp emission features. These lines allow astronomers to determine not just which elements are present, but also how they're distributed in the expanding cloud. Sometimes we even see forbidden lines, transitions that aren't allowed under normal laboratory conditions on Earth because they occur so slowly that collisions would usually interrupt them. But in the thin, low-density environment of a supernova remnant, these lines can occur. They're called forbidden, not because they're breaking any rules, but because they're just very shy, visible only in the quiet solitude of space. Their presence helps identify elements like oxygen, neon and sulfur in the cooling cloud. Supernova spectra don't just reveal chemistry, they tell us about geometry and physics too. For example, if the explosion is asymmetrical, or if jets of material are being launched in particular directions, that can show up in the shape and shift of the lines. Small asymmetries in the explosion can create doppler shifts that cause the spectral lines to skew or split. These features help astronomers reconstruct how the blast unfolded. In rare cases, astronomers are lucky enough to catch a supernova very early, within hours or even minutes of its initial light. These observations, though difficult to obtain, are gold mines of information. Early spectra can capture the shock breakout, the moment when the explosion first punches through the surface of the star, and reveal fleeting features that disappear within hours. It's like seeing the very first page of a book that usually starts at chapter 2. Even long after a supernova has faded from view, its light continues to echo. In some parts of the galaxy, astronomers observe light echoes, reflections of the original explosion off nearby dust clouds. These echoes arrive later than the direct light, like the reverberation of a shout bouncing off a canyon wall. By analysing the spectrum of these echoes, scientists can restudy old supernova from a new angle, sometimes decades after the original event. Famous supernovae like SN 1987A, which exploded in the Large Magellanic Cloud in 1987, have been monitored for years. Its changing spectrum has provided an ongoing education in stellar death and rebirth. Even now, its light is teaching us about how material interacts with its surroundings, how supernova remnants evolve, and how new elements are distributed into the galaxy. All of this, from the blinding flash of the explosion to the faint whisper of a cooling remnant, is captured in light. And not just any light, but structured, detailed, exquisitely informative spectra. They don't just tell us what blew up, they tell us how and when and what was created in the process. In the end, a supernova is both an ending and a beginning. It marks the death of a star, but also the birth of new elements, new possibilities, and perhaps even new solar systems. And long after the blast has faded, its story lives on, in the spectral fingerprints it leaves behind, still glowing, still telling the universe what it became. Light is many things. It's a wave, a particle, a carrier of energy, a painter of sunsets, and a whisper from across the universe. But perhaps one of its most curious qualities is that it's always running late. Not because it's slow, it's actually the fastest thing there is, but because space is just that vast. The distances between stars and galaxies are so enormous that even light, racing along at nearly 300,000 kilometers per second, takes its sweet time getting to us. And that simple delay turns our telescopes into time machines. It sounds like science fiction, but it's pure, elegant fact. When you look into the night sky, you are literally looking into the past. The farther away something is, the longer its light has taken to reach you, and the older the picture you're seeing. It's as if the universe has left a trail of old postcards, each one travelling at light speed, arriving on Earth in a steady stream and saying, "Here's what I looked like when I sent this." When you gaze at the moon, you're seeing it as it was about 1 1/3 seconds ago. That's how long it takes for moonlight, actually reflected sunlight, to travel the roughly 384,000 kilometers to Earth. When you look at the sun, you're seeing it 8 minutes and 20 seconds in the past. If the sun were to mysteriously vanish right now, don't worry, it won't. We wouldn't notice for over 8 minutes. But as you look farther out, the numbers start to stretch dramatically. The nearest star system, Alpha Centauri, is about 4 light years away. That means its light has been on the road for 4 years before it reaches your eyes. If you could somehow watch a planet orbiting one of those stars, you'd be watching a recording from 4 years ago, not a live feed. This delay turns into something extraordinary when we point our telescopes beyond our local neighbourhood. The Andromeda Galaxy, our nearest major galactic neighbour, is about 2.5 million light years away. That's 2.5 million years of travel time for its light to reach us. The image we see of Andromeda is what it looked like back when early human ancestors were first experimenting with stone tools. Push the telescope deeper into space, and we reach even further back in time. Some of the galaxies detected by the James Webb Space Telescope are over 13 billion light-years away. Their light began its journey when the universe was less than 5% of its current age. The cosmos was still in its childhood, hotter, denser and more chaotic than the gentle spirals and elliptical galaxies we see today. This concept is one of the most mind-stretching and delightful aspects of astronomy. The sky is not just a spatial map, it's a temporal map. Looking up is also looking back. Every dot of light, every fuzzy galaxy, every faint smudge in the black is a message from the past. And every telescope, no matter how small or mighty, is a kind of time traveller, collecting ancient photons and translating them into a cosmic history book. What makes this even more remarkable is how precise this fossil record can be, because light carries information, not just about brightness, but about wavelength, composition and motion. We can use it to study what things were like billions of years ago with surprising clarity. Light from early galaxies tells us how stars formed when the universe was young. It shows us the first heavy elements forged in stellar furnaces. It lets us see cosmic structures assembling like bricks in a slowly rising cathedral. When we look at the most distant galaxies, we're peering into a time when the first stars were igniting. These primordial stars, massive and short-lived, are thought to have formed from pristine clouds of hydrogen and helium left over from the Big Bang. Their light, stretched and redshifted by the expansion of the universe, arrives at Earth after a journey of billions of years. That light doesn't just show us where those stars were, it shows us what the universe itself was becoming. This is why astronomers talk about look-back time. It's a way of measuring not just distance, but age. A galaxy 10 billion light-years away is seen as it was 10 billion years ago. A quasar from 12 billion light-years away is a time capsule from an era when galaxies were just beginning to take shape. The cosmic microwave background, the faint afterglow of the Big Bang itself, is the oldest light we can observe, dating back over 13.8 billion years. It's the universe's baby picture, and it fills the sky with a quiet whisper of ancient heat. In this way, astronomy becomes a kind of cosmic archaeology. Just as paleontologists dig through rock layers to uncover fossils from Earth's distant past, astronomers sift through layers of light, each one older than the last. The difference is that their tools are not shovels and brushes, but mirrors, lenses and spectrometers. They don't uncover bones, they uncover photons, and every photon carries a clue. Some of the most dramatic time-travelling observations involve objects that have changed dramatically over cosmic time. Take galaxies, for example. Nearby ones tend to be calm, structured and mature. Their stars orbit smoothly, their shapes are stable, and their star formation rates are often low. But in the deep past, we see a different universe, one filled with irregular, clumpy galaxies in the middle of forming themselves. There's more gas, more starbursts, and more collisions. Galaxies were wilder then, more chaotic, like toddlers learning how to walk. By observing galaxies at many different distances, and thus many different ages, astronomers can reconstruct the history of galaxy formation. It's like having a photo album, but instead of snapshots of one object through time, you have snapshots of thousands of galaxies at different ages, each one offering a piece of the puzzle. Even stars leave their timestamps in light. Supernovae, for instance, explode and fade over weeks or months, but their light can continue to travel for millions or billions of years. When that light finally reaches us, it tells us about an explosion that happened long ago in a far-off corner of the universe. We can even catch light echoes, reflections of a supernova's flash off nearby dust clouds, arriving years after the main event like a cosmic encore. And then there's the thrill of discovering objects right on the edge of visibility. The first galaxies, the first quasars, the first supermassive black holes. These ancient light sources are not only faint but stretched by the expansion of space itself. Their light is redshifted far into the infrared, which is why instruments like the James Webb Space Telescope were designed to see in that wavelength range. They're essentially tuned to pick up whispers from the earliest chapters of the universe's story. All of this brings a strange kind of intimacy to the universe. We're not just seeing distant places, we're witnessing ancient moments. The light from a galaxy 10 billion light-years away is arriving now, in your lifetime, after travelling undisturbed through the void since before the Earth had oceans. It's as if the cosmos is gently handing you a story it has been carrying for eons. And perhaps most wonderfully, this story is still being written. The universe continues to shine, to evolve, to send out photons that will someday reach distant observers in some future epoch. Maybe a civilization a billion years from now will study the light from our galaxy as it looks today. To them will be a deep sky object, glowing softly from across time. So whenever you look at a star or a galaxy or a hazy smudge in the sky, remember, you're not just seeing where it is, you're seeing when it was. The sky above you is a layered, glowing timeline of the universe itself, and every point of light is a messenger from long ago, arriving just in time to be seen. In the beginning, before galaxies had settled into elegant spirals and before the periodic table had more than just a few names on it, the universe was a dark, expanding sea of simplicity. There were no planets, no iron, no carbon, no gold, just clouds of hydrogen, a dash of helium, and a trace whisper of lithium. Nothing else. But eventually gravity began to stitch these elements together into something new. From this blank canvas, the first stars were born. These earlier stars, known as Population 3 stars, are the most ancient actors in the cosmic play, and yet we've never seen one directly. They lived and died long ago, leaving behind no light we can point to with certainty, at least not yet. But their existence is almost universally accepted, not because we've captured their images, but because the story of the universe makes no sense without them. And now, thanks to advances in infrared astronomy and deep sky observation, we're getting closer than ever to catching a glimpse of their spectral ghost light. To understand why Population 3 stars are so special, it helps to know a little about the population system astronomers use. It's a bit of an odd naming convention, in that it starts backward. Population 1 stars are the youngest and most metal-rich, like our Sun. These stars have been formed from the recycled debris of countless stellar generations and are rich in elements heavier than helium, which astronomers charmingly refer to as metals. That includes everything from carbon and oxygen to iron and uranium. Population 2 stars are older and poorer in metals. Many reside in the halo of the Milky Way, or in ancient globular clusters. These stars formed early in the universe's history, from gas that had only been lightly seasoned by the very first supernova. Then we reached the enigmatic Population 3 stars, the theoretical firstborn. These stars would have been made from pure, unpolluted hydrogen and helium, forged in a cosmos that had not yet known heavier elements. The absence of metals would have made them fundamentally different from any stars we see today. And while no confirmed Population 3 star has yet been observed, scientists believe they were massive, perhaps dozens or even hundreds of times the mass of our Sun, and burned with extraordinary brightness and heat. Why so large? It turns out metals, again, anything heavier than helium, help cool collapsing clouds of gas, allowing them to fragment and form many smaller stars. In a metal-free environment, cooling is far less efficient. This means the gas collapses into fewer, much larger stars. These giants would have lived fast and died young, lasting only a few million years before exploding as supernovae or collapsing directly into black holes. Because they were so short-lived and existed so early in cosmic history, direct observation is tricky. We can't just scan the skies and find one twinkling quietly in some remote corner of the galaxy. Their light faded billions of years ago, but like archaeologists searching for ancient bones, astronomers are learning to detect the subtle traces these stars may have left behind. The best clues come from light itself, or more precisely, from the absence of certain kinds of light. When a star forms, its spectrum, its unique pattern of light, is shaped by the elements in its outer layers. Metal-rich stars show a forest of absorption lines: calcium, sodium, magnesium, iron, and more. Metal-poor stars show fewer lines, and the lines they do have are shallower. A truly metal-free star, like a Population 3 star, would produce an extraordinarily clean spectrum, showing only the fingerprints of hydrogen and helium. This theoretical spectrum has been modelled in great detail. Scientists have created simulated profiles for what a metal-free stellar spectrum should look like, accounting for temperature, pressure, rotation, and other factors. If we could spot such a signature in the sky, an unusually hot star with a smooth, clean spectrum missing all the usual heavy element lines, it would be a strong candidate for a Population 3 star or a cluster of them. But there's a catch. The light from such stars, if it still exists at all, would be redshifted. Very redshifted. Because they lived over 13 billion years ago, their light has been stretched by the expansion of the universe into the infrared part of the spectrum, far beyond what most telescopes can see. That's why missions like the James Webb Space Telescope are so crucial. James Webb was specifically designed to look back to the earliest epochs of cosmic history. Its infrared eyes are tuned to catch the redshifted light from the first stars and galaxies. Already, Webb has identified candidate galaxies from when the universe was less than 400 million years old. a time when population 3 stars might still have been shining. What Webb and future telescopes are searching for are galaxies with extremely low metallicity, places where no or very few heavy elements are detected. These galaxies may still host patches of gas untouched by previous generations of stars, giving birth to new stars that are essentially metal-free. We may never see a single, isolated population 3 star, but we might observe the combined light of a small group, glowing faintly from the distant reaches of time. There are also indirect signs. Some astronomers believe that certain supernova remnants in ancient galaxies may be the fingerprints of population 3 deaths. These explosions would have produced unusual elemental ratios, not the familiar iron-rich patterns of modern supernovae, but exotic blends dominated by lighter elements like carbon and oxygen, and very little of the heavier stuff. Additionally, some of the most metal-poor stars in the Milky Way halo may be the children of population 3 stars. These ancient survivors, now quietly burning in the outskirts of our galaxy, may have formed from gas that was just barely enriched by the supernovae of the first stars. By analysing their compositions with high-resolution spectroscopy, scientists can reverse engineer what must have come before them. And then, of course, there's the possibility that some population 3 stars didn't explode at all. If a star was massive enough, over 200 times the mass of the Sun, it may have collapsed directly into a black hole. These early black holes could have grown over billions of years into the supermassive black holes we now see at the centres of galaxies. Some of the quasars we observe burning brightly across cosmic time may be powered by the dark remnants of the very first stars. The search for population 3 stars is a blend of science and detective work. We can't spot them with a backyard telescope. We rely instead on patterns, ratios, and missing ingredients. It's a bit like trying to learn about the first humans not by finding their bones, but by studying the tools their descendants inherited and improved. Even the silence in their spectra, the quiet absence of metals, speaks volumes. This is part of what makes astronomy so beautifully strange. In most sciences, the older something is, the harder it is to reach. But in astronomy, old light is still travelling. It hasn't aged or faded in its message. The photons sent by the first stars are still en route, crossing the universe, slipping past galaxies and clouds and comets, heading toward our detectors, our mirrors, and our minds. Somewhere out there, in the red-stretched glow of the early cosmos, the first stars still shine, at least in light that hasn't arrived yet. The search continues. With every new observation, we inch closer to meeting our cosmic ancestors face to face, or rather, light to eye. And when that day comes, the universe will have whispered to us the opening line of its longest, oldest story. When we look up into the night sky, it's easy to see the stars as simple points of light, distant, beautiful, and silent. But they are anything but silent. Each one is speaking. Each flicker, each glow is a message sent across the darkness, travelling for years, centuries, even eons, just to arrive at this moment, at your eyes, or at the mirror of a telescope. Starlight isn't just illumination, it's communication. In every beam of light is a story. A star's colour tells us its temperature. Its spectrum tells us what it's made of. Shifts in its lines reveal how it moves, how it spins, how it wobbles, whether something is tugging at it unseen. We can hear the whisper of an exoplanet by the slight dimming of starlight. We can measure the birth of galaxies, the death of stars, and the echoes of the Big Bang itself, all from the way light behaves. This is the quiet brilliance of the cosmos. It talks in photons. And if we learn to listen, to read, to gently decode what each wavelength is saying, we uncover everything. Light becomes a time machine, a thermometer, a chemistry lab, a cosmic GPS. From the fiery beginnings of the first stars to the elegant spiral of a galaxy billions of years later, it is light that brings us the news. Even the oldest light, the faint glow from the edge of the observable universe, still has something to say. And as we build better instruments, peer deeper into space, and refine our models, we are slowly becoming fluent in this strange, beautiful language of the stars. Perhaps that's what makes it so calming, so peaceful to gaze up at the sky. It reminds us that the universe isn't indifferent. It's not mute. It speaks. It just speaks slowly, softly, patiently. And all we have to do is open our ears, or rather our detectors and our minds. So as you drift off tonight, perhaps you'll think of starlight a little differently. Not just as a sparkle or a shimmer, but as a message sent long ago, still travelling through space to find you. It's the universe, whispering its story, one photon at a time. And before we end, I'd love to hear from you. Where in the world are you watching from tonight? What's your local time as you unwind with the stars? Let me know in the comments below. And if this quiet journey through the cosmos helped you feel just a little more connected to the night sky, please consider leaving a like or subscribing to The Sleepy Scientist. It really helps more curious, sleepy minds find their way here. And remember, while this video might help you rest, it is not medical advice. But if it kept you awake because it was too interesting, well, at least you learned something along the way. Sleep well, the stars will keep shining,